All right, folks, welcome back. We're going to move into section number 5 in our OSPF discussion. In this section, we're going to talk about a lot of things that I kind of alluded to when we were talking about in module 4, which is, yeah, there's a certain way to implement OSPF, but if you want that reliability, if you want that fast convergence, if you want that scalability, then you're absolutely going to want to incorporate some of the enhanced features of OSPF. And some of those optimizations include things like summarization, special area types. We're going to talk about that in this section as well as talking about authentication to enhance the security. We know that OSPF is a linked state routing protocol, and as such, in order for it to scale to the environment that we want, we definitely need to make improvements on how information is shared between the routers and how we can reduce the amount of information that goes into our linked state database. In addition, we want to be able to reduce the amount of LSA flooding that occurs in the domain by essentially creating these natural boundaries or these natural barriers for that linked state flooding to occur. So we're going to talk about that in this section. We're also going to talk about these special area types. Special area types are used in the case of OSPF to identify the types of LSAs that are allowed to enter a particular area. Stubby areas, totally stubby areas, not so stubby areas, and totally not so stubby areas. And we'll break down what each of those special area types represent, why I would consider using one special area type versus another. Again, the whole point of adding this efficiency is to reduce the amount of overhead on our linked state database, to reduce the size of that database, that OSPF routing information base, but still maintain that reachability that we need, still maintain the reliability that we need, and so on. And so we'll take a look at different use case scenarios for these special area types. We'll be doing a discovery as well, where we're going to configure and monitor and assess how those special area types affect the size of our databases and our routing tables and so on. We also know that in general that default routing is always something that we can consider to reduce the size of routing tables. Obviously, default routing is not going to be necessarily the end-all be-all in OSPF or any routing protocol for that matter, because it reduces essentially our visibility of the network down to a single route. But certainly in certain cases, default routing is going to be more preferred. And we'll talk about how we control and manage default routing in OSPF. It is slightly different than what we saw with EIGRP as to how we originate routes in OSPF, default routes in OSPF, as well as how we kind of manage that cost of those routes and so on. So we're going to take a look at summarization as well. We know that from our previous discussions in Module 4 that we can only summarize on two different types of routers in OSPF, on area border routers and autonomous system boundary routers. And we also learned in the EIGRP module how summarization can vastly improve scalability and the limits, and how it could limit the need for recalculating databases and running algorithms. But again, there's some very specific things to consider when you are doing summarization. We'll explore the concepts of summarization during the lecture, and then we'll look at some of the implementation of summarization and some of the key things to look out for when you're implementing summaries in a dynamic routing process like OSPF. And then finally, our last topic, we will be discussing authentication. And we'll take a look at authentication from the perspective of OSPF v2, as well as from the perspective of OSPF v3. Not only the classic OSPF v3, but the address family implementation of OSPF v3. Just as a quick summary, what we're going to be discussing in this lecture or in this module is what are the properties of OSPF route summarization, how can I implement it, where can I implement it, what are some of the guidelines that I'm going to use, what are the benefits of route summarization, how do I configure summarization on my area border routers using the area range command, and how do I configure summarization on my autonomous system boundary routers using the summary-address command. How can I affect the default cost of a default route? and how can I manipulate that so that I can maybe prefer one default path over another default path. And then how do we implement default routing with special area types? Well, not only special area types, but just stub routing in general. Typically with stub routing, we'll use a default route as an egress route, and we'll use dynamically learned routes as, well, let me say that again from the perspective of the stub network. We'll use a default route to get out, right? And we'll use dynamically learned routes to learn what is available on the outside, but those dynamically learned routes will come in. So again, both routes are used to exit the domain, but one route is learned internally and one route is configured through the OSPF process. What are not so stubby areas? Well, we're not just going to talk about NSSAs. We'll talk about stub areas. We'll talk about totally stubby areas and totally not so stubby areas as well. And then we'll wrap up the module by discussing OSPF authentication. What are the options for OSPF v2 and v3? Both v3 classic and v3 address family mode, because there are some significant differences in that case. We'll actually do a discovery that incorporates that as well. And then finally, our final lesson of the module, we'll be talking about virtual links, why they are necessary, and how we can configure them in the various versions of OSPF. So let's start by discussing OSPF route summarization. Now, we have discussed many times, not only in our general routing concepts and general routing processes, but also specifically with OSPF, we've talked about the benefits of summarization, right? The concept of taking lots and lots of longer prefix length routes, meaning more bits in the mask, and summarizing them and representing them as a single or at least fewer shorter prefix routes, right? That's the whole point of summarization. Summarization allows me to take a bunch of smaller routes and consolidate them into a larger route. Now, in order for summarization to be effective, and in order for us to be able to effectively implement summarization, we have to have contiguous address space, meaning that networks A, B, C, and D might have to be in area 0, and networks E, F, G, and H would be in area 1, and they would be represented numerically in order, so we don't have discontiguous subnets across our enterprise. We already know from our previous discussions that we have different LSA types that get generated in this network. For example, we're going to have type 5 LSAs coming in that represent those external EIGRP routes, and we can summarize those type 5 LSAs, right? In fact, ASBR is one of those routers that we can summarize. So if I have, 100 different external routes that exist in that external domain, I can simply summarize them as an individual route, assuming that those external networks are contiguous and there's not going to cause any kind of suboptimal routing selection in my OSPF domain by using an invalid summary. All right. In area 1, we're going to have, of course, our type 1s, most likely some type 2s as well. Those are intra-area LSA types. Well, those are ultimately going to be sent into the backbone area as type 3s. So again, we can summarize those type 1s and type 2s on our ABR into our backbone. Now, the key thing about implementing these summaries is that you want to make sure that you're implementing the summaries in a way that it doesn't cause routing confusion or it doesn't introduce suboptimal routing within your domain. In this topology, that's relatively simple because we have essentially stub links between all of these areas. There's only one way in and one way out. But when you start to implement multiple ABRs or even possibly multiple ASBRs in your topology, there are some other things to consider when you're implementing these summaries. So we'll take a look at that. We won't really see it in design. We're going to have a pretty basic implementation in our discovery, but I will talk about those concepts when I go through the discovery a little bit later on. So route summarization is the consolidation of those contiguous address spaces on an ABR that's done using the area range command. We'll see that a little bit later, and we're going to summarize those type 1s and type 2s into type 3s. Now those type 5s will propagate through the domain and they'll enter area 0 as type 5s as well. So the summarization is critical. It's going to happen at that point in the topology. I'm not sure why my pen is acting weird, putting all those weird lines there, but you get the idea. All right, so we're going to talk about how do we consolidate address space on an ABR by using the summary address or area range command, and how we do it on an ASBR by using the summary address command. As the third bullet point mentions, it is very, very important to have a good addressing plan. You don't want to have network A over here and network B over here and network C over here and network D over here and so on. You want to make sure that your network address space is contiguous. If you don't have contiguous address space, it becomes practically impossible to gain the benefit of summarization, because you can't summarize to very large boundaries or you can't summarize at all. So it may require some readdressing in your network or some pre-planning if you're implementing a greenfield environment to make sure that you have that appropriate address space configured. All right. The drawback of summarization is always suboptimal routing, particularly if you don't have contiguous address space. A summary route always has a shorter prefix than the individual routes that it summarizes. And Networking 101 states that when a router is routing, the router will always route using the longest prefix match. So a summary route may not always be matched if there happens to be a longer prefix match for that particular destination. So you could have a situation where a summary route might point one direction, but you may have leaked out or learned from another client, another peer, individual route that's part of that summary, and that individual route would always be used. Again, we'll talk about that as we go into the discovery. I'll demonstrate some of the things that you need to consider when you're dealing with these summaries. All right, but the whole point of summarization: shrink the size of the database and reduce the amount of LSA flooding, right? For example, if I'm summarizing 20 networks from area 1 to area 0, and one of those 20 networks goes down, the summary into area 0 doesn't change. The summary into area 0 is the same, which means that we don't have to recalculate our database, okay? So a couple of other points here. I just want to make sure I'm hitting up these paragraphs. We've already talked about this. Intra-area prefix type 1 LSAs, which are my router LSAs, and intra-area prefix LSAs, type 2 LSAs are my network LSAs. I'm not sure why they referenced prefix and router there. Technically, a type 1 LSA is referred to as a router LSA, and a type 2 LSA is referred to as a network LSA, but in any event, that's what they're representing. They are intra-area. They're going to be generated inside of the area, and then they will eventually get converted to inter-area prefix LSAs. All right. Now with route summarization, we want to obviously consolidate as many of those external route or those individual routes as we can within the summary, and that requires, like I said, good addressing and good networking design initially. All right. Now, remember what I said yesterday when we were talking about kind of OSPF architectures, right? I said if you have a single area OSPF implementation, you're going to lose the ability to do summarization. Well, that's because you don't have any ABRs, right? You may still have ASBRs, and of course, you'll always be able to do summaries on an ASBR, particularly with single area implementations, because you're going to be connecting that ASBR to area 0, which can never be a special area type. So you'll be able to do summarization on that router, but you're not going to be able to do summarization on any ABRs because you simply won't have them. So a lot of times we will design that spine and leaf topology to make sure that we have that capability of doing summarization. Okay? Now there's two different types of summarization that we can include. And we've mentioned this already a couple of times. Summarization of those internal type 1 and type 2 LSAs on a area border router that get represented as type 3s, and summarization of those external routes on an ASBR that get represented as type 5s. All right, there are a couple of things to consider when we're generating the summary, and these are actually really, really important bullet points. right? So let's say, for example, I have, 6 or 7 different networks that I'm trying to summarize in area 1, and I'm summarizing those into the backbone. Each of those individual routes in area 1 have their own metric, right? Some of them might be the same, some of them might be different, but ultimately you're probably never going to see the same metric for all 7 routes. So when you're performing the summary, particularly if that summary includes all of those prefixes, we're going to be sending in this individual type 3 route. The question is, what metric do I place on that type 3 route? Do I do some mathematical calculation and create some mean value from all of the values of the individual metrics on the individual routes? Well, the answer is I take the lowest cost of all of those individual 7 routes. So cost 10, cost 20, cost 30, cost 100, cost 70, cost 50. Ultimately, the cost of the type 3 route is going to be cost of 10. And that's, by the way, the same with EIGRP. We always our cup is half full, I guess. We assume that the metric for the summary is automatically going to be the metric for the lowest metric for the routes that are included in the summary. In order for this summary to be generated, we have to have at least one route that's available in the global routing table of this router that is part of that summary. So if I'm summarizing these 7 networks and 6 of them go down, I will still be generating the summary because I still have an active route, albeit a longer prefix. I'll still have an active route that is part of that summary range. As soon as that 7th route goes away, though, we will lose the summary. The summary will still be configured in our global configuration, but we will lose the summary route. It will no longer be propagated by the ABR. Okay? This last bullet point, also very, very critical, the null zero route. We saw that in EIGRP. We will see that in OSPF as well. Okay? So when I do my summaries on this ABR, and I am summarizing those 7 prefixes, let's just say all those 7 prefixes have a /24. Okay, and I happen to be summarizing those into my backbone as a /16. All right, so my summary, obviously that's a pretty broad summary, probably not maybe that broad, but if there's no overlapping subnets in the topology, that would be okay. I'm going to be advertising that /16 that includes those 7 /24 prefixes, well, 5 in this case, but going back to our original discussion, 7, right? But the ABR is going to do something very special because this /16 ultimately would include other prefixes that this ABR doesn't actually have, right? /16 is a much a kind of larger network than the individual /24s. And if I only have 5 different /24s, then clearly there are going to be other subnets that are included in that summary. So router 1 and the other routers in OSPF are going to think that they can get to all of those networks in that /16 range, even though they don't exist. So as a loop avoidance mechanism, the ABR is going to generate a local null zero route that matches the summary. X/16, network X/16. And I don't know why these lines are going all crazy, but hopefully you guys can follow along here. I think it has to do with the WebEx, because when I was doing this before, it wasn't doing that. So I don't know if WebEx is messing something up or whatever. But in any event, the ABR generates that local null zero route. You will see that in the routing table, and it will match the summary that you created. So if somebody, let's say this is network A, B, C, D, E, right? A through E. And over here, somebody thinks that they can route to network F. Let's just say network F. It doesn't really exist, but it's part of that /16 broadcast domain, right? So that traffic will go to the ABR, but the ABR doesn't have an F network. However, it has this null 0/16, which includes F. So that packet will get routed to that null zero interface, and the packet will ultimately get dropped. And that's the loop avoidance mechanism. So that null zero concept, really, really critical as a loop avoidance mechanism anytime we're doing summarization. Doesn't matter what routing protocol, it's always going to be there. We saw that in EIGRP, and we're going to see it in OSPF as well. All right. Now, without the summarization of the type 1s and 2s, what's going to end up happening is we will end up generating type 3s for all of the type 1s and type 2s. There is no automatic summarization that occurs on the ABR. So if I have 1,000 type 1s in area 0 or area 1, I'm going to end up having 1,000 type 3s in area 0. So that's obviously one of the main reasons why we even consider doing these summaries, is because we want to make sure we're reducing the amount of routes that get propagated. And of course, we want to make sure that we're reducing the need to recalculate our database if something changes. That internal summary route, like I said, gets generated as long as we have one network that falls within that summary range. We'll use the lowest cost, and there will be a null zero route that gets created for loop avoidance automatically. All right. To create the summary address, and we'll see this in the discovery as well, on OSPF v2, we go into our ABR and we use the command area range. That's under the router configuration mode. So I go in config T, router OSPF1, area range, and then I'm going to specify the area from which I am summarizing, not to which I'm summarizing. All right, I'll make a point to note that when we see this in the discovery as well. We're always specifying the area that's originating the routes being summarized, not the area we intend for the summary to be propagated into. Okay, bad English there, but you get the idea. In OSPF v3, we do the same command, area range, and again, it's always the area that we're summarizing from. But obviously that's going to be under our router OSPF v3 configuration as opposed to the router configuration. On an ASBR, same kind of rules apply, right? The summary will get generated as long as there's one prefix that's included within that scope. There will be a null zero route created, and the metric that is going to be used for that type 5 LSA is going to be based on the lowest metric for the route. Actually, that's not entirely true. I'm going to explain why that is a little bit later on. It kind of makes sense, right? If I'm coming from OSPF and going to OSPF, as in an ABR summary, then the metrics are compiled, in a similar fashion, right? We're using the same calculation. Even though the metrics might be different, we're using the same mathematical calculation, so we're comparing apples to apples. When you're summarizing external routes. Now, these are routes that are coming from external routing domains. That's not always the case, right? Yeah, you might be redistributing EIGRP into OSPF, but you also might be redistributing connected routes, static routes, and that summary could include a mixture of routes. So actually, there are going to be some default metrics that get applied when you do the redistribution. And it depends on where it's coming from. Typically it's, and you know, it'll depend on how those metrics get propagated will depend on whether they're being redistributed as a type 1 external route or a type 2 external route, not LSA type, but external route type. We'll get into that later on as well. Has to do with how the metric is calculated and propagated. But the only way that we're generating those type 5 LSAs is through the process of redistribution. And by definition, redistribution has specific rules on as to what the seed metric is going to be for the routes that are being redistributed. You know, this concept of lowest metric doesn't even apply in this case. Even though I kind of started to go down that path, I realized, that doesn't really make sense based on how it actually works. And we'll see that a little bit later on as well. All right, to create the summary address in OSPF v2, again, we go on our ASBR, and we use the summary-address command. Again, this is under router configuration mode. If you recall, when we were doing summaries in EIGRP, it was an interface configuration command, or in the named mode, it was at least an AF interface configuration command. With OSPF, it's done under the router configuration mode. And we will specify, we don't really specify the source area because obviously there is no source area. These routes are coming from an external routing domain. So we'll use the summary-address command, very similar to the syntax that we saw with EIGRP, but not quite the same. All right. Make sure you have contiguous address space. We've talked about that multiple times. Now, how do we handle default routing in OSPF? Default routing does play a significant role in most enterprise networks. Usually a default route is going to be used to route towards the internet. So that's going to be a pretty important concept. We can't really capture all of the routes from the internet, so it's important for us to use that default routing. Now, there's a couple ways that we can inject a default route into OSPF. The preferred method is to use a command called default information originate. And default information originate can be implemented in a couple of different ways. We'll explore those options when we get into the discovery, but essentially default information originate is like telling OSPF, it's almost like a macro, although it's not a macro. It tells OSPF to redistribute a quad 0 route into OSPF. Okay? Now, that default route could exist on that ASBR. For example, that ASBR might have a default route that points to the service provider router. And so I would simply have maybe a static default route that points to the internet, and then I would go into my router configuration mode or my address family configuration mode, and I would say default information originate. And then that ASBR would start generating, notice, type 5 LSAs, into the area. So that's like a redistributed route in OSPF. And that would propagate through the entire domain. It would even go into here as a type 5 with the exception of the fact that this is a special area type. It is a stub area, and external routes are not allowed into any special area type, let alone a stub area. We'll get into that later on. Obviously, the whole point of a default route is to be able to reach the destinations that fall beyond our enterprise, the hundreds of thousands or millions of routes that might exist on the internet. It's not really practical to have all those routes injected into our internal domain. Okay? Now, default information originate does not have to be implemented on an ASBR. Well, let me rephrase that. By implementing default information originate, you're essentially making that router an ASBR because it's always going to generate type 5 LSAs or potentially type 7s if it's an ASBR and an NSSA or totally NSSA. So if you did default information originate on router 4, it would become an ASBR and so on. So by the fact that we implemented the command makes that router an ASBR. Now it may be an ASBR for other reasons, like doing redistribution of other routing protocols, but the default information originate is like a redistribution, even though you're not really doing a redistribution command. Okay? We can inject the default route using type 5 LSAs, which is what the default information originate command does. And when we go into talk about special area types, default routes can be injected by using special area type configurations. There are three of the 4 special area types automatically generate a default route into the area that's configured as a special area type. And we will definitely see that a little bit later on. All right, when we get into our discussion about the special area types. All right, now notice some of the options that we have here with default information originate. We have default information originate by itself. When you implement default information originate by itself, a default route will be advertised as a type 5 LSA into OSPF, but only if that router has a default route itself. Okay? So if I have a static default route that points to the internet and I run the default information originate command, the default route will be injected into OSPF. But if I take away that static default route, that default route will no longer be propagated. If I use the always keyword, When I specify the always keyword, that means that router 4 will generate a default route into OSPF regardless of whether or not it actually has its own default route pointing to the appropriate destination. You'll see a couple of other things here. A route map, that's a little bit beyond the scope of what we're talking about right now. We will talk about policy-based routing and route manipulation a little bit later on. But I can apply a route map to this default information originate, which gives me a lot of flexibility on manipulating that default route. Metric type would be either type 1 or type 2, and E1 or E2 in this case. And we'll get into that a little bit later on as well, how metrics are manipulated. And then the metric keyword would allow me to specify the seed metric for that default route, right? If I'm redistributing from BGP, it will come in as a 1. If the seed metric, if I'm redistributing from other routing processes, it would come in with a cost of 20. But we can manipulate that by using the metric keyword. And again, all this stuff we're going to see as we go through our discovery a little bit later on. Okay? So the last thing that we're going to talk about in this section before we actually get into that discovery are what are these special area types. Now in Cisco's world, yeah, you have to remember OSPF is a open standard routing protocol. Okay? And if you go look at the original RCs for OSPF, there are a couple of concepts that they define in OSPF, but they don't really define how they're supposed to be implemented. The metric, for example, it is defined in the RC that the metric is supposed to be a cost value, but it's actually up to the manufacturer and the vendor to decide how that cost is calculated. Cisco happens to use 10 to the power of 7 divided by the link bandwidth in bits per second to calculate cost. Other vendors might use different methods. Well, in the case of special area types, some of these special area types were defined in the RFC, and some of them are, well, at least one of them is proprietary to Cisco. And we'll see that in the lecture portion here. The purpose of a special area type, like a stub area or totally stubby area, is to limit what is allowed to go into that special area at the ABR. All right, so ABR2 in this example is configured as a standard area. Well, it's attached to a standard area. And that means that pretty much everything is allowed to go into Area 51. ABR1 is configured as a stub area. And you can see from the diagram here what is not allowed to go into the stub area. Type 5s are not allowed into the stub area. External LSAs. We still have our 1s and 2s internally. We still have our type 3s that come in. But type 5s are not allowed. All right. Now, again, the purpose of this is to essentially reduce the size of our databases and reduce the impact of the loss of these links externally on recalculations of the link state or the sorted SPF algorithm in Area 50. But I still want to be able to route to those external routes. I still want to be able to get to those external domains. I may not have visibility as to what they are individually, but I still want to be able to route to them. So the ABR in this case will automatically start generating a default route into Area 50. And that default route will actually come in as an OIA route, a type 3, because type 3s are allowed. Now, what else is not allowed in a stub area? ASBRs are not allowed in a stub area. You cannot have an autonomous system boundary router in a stub area. Now, we'll talk about the other 3 scenarios, but the reality is, what do I choose, right? If ABR1 is really the only router that is connecting Area 0 to Area 50, then I might as well just make the area totally stubby. There's no reason not to. We'll see what totally stubby does a little bit later on. Your decision on what type of special area you implement will really be determined based on what your goals are and how you're trying to reduce the overhead in OSPF. We'll certainly explore all the options, but you'll see very quickly there's not a whole lot of difference between stubby and totally stubby. In a stub area, though, let me scroll down here, get to the rest of the bullet points here. In a stub area, external LSAs are not allowed. A default route is automatically advertised into the stub area by the ABR. By the way, we set the area as a stub, not a router. In EIGRP, we talked about stub routers for query scoping, but in that case, it was the individual router that was actually really not the router. It was the neighbor relationship that established the stub. Actually, it was the whole router, sorry, that was propagated to the neighbors. But in OSPF, it's the entire area. So if one router in the area is configured as a stub, all the routers in the area have to be configured as a stub. All right? Again, we typically will do this if we have a hub and spoke topology or we have a stub network, meaning we only have one way in and one way out. We haven't seen the configuration yet, but we'll take a look at that in a minute. What about a totally stubby area? So again, totally stubby means no ASBR. So you cannot have an ASBR in area 50. Totally stubby means nothing is allowed in. Summary routes are not allowed in. External routes are not allowed in. Internally, you're only going to have type 1s and 2s. And then you're going to have a default route that gets sent into the totally stubby area so that you have reachability to the rest of those prefixes. But you just won't be able to see them individually in the routing table. And this is what I was talking about previously. If I'm going to make an area a stub, which blocks external routes, type 5s, then most likely I probably would benefit from just making the area totally stubby. Unless there's some particular reason, for some policy or some other reason, you would want to have the type 3s show up, individually, and then you would configure the area as a stub. So by definition, nothing is allowed into the area. Only the default route is advertised. This is a Cisco proprietary feature. All right, Cisco proprietary. So again, that's one of those things that I mentioned previously. Some of these features are part of the RFC, and some of them are developed by Cisco. All right. So, and we never talked about type 4s. You can assume, by the way, if type 5s are not allowed into an area, type 4s would not be allowed into an area. We didn't talk about that in the stub configuration, but type 4s are directly related to type 5s. If you're not getting type 5s, there's absolutely no reason to get type 4s. All right. Totally stubby area, again, will minimize the size of the database and minimize the effect of the loss of particular links. A not so stubby area. Well, let me say not so stubby is in essence the same thing as stubby, with the exception that you have the ability of attaching an ASBR to that area. That's what makes it kind of not so stubby. All right, so the orange area in the middle, orange, yellow, kind of orange and yellow. That area in the middle is configured as an NSSA, which means you are allowed to have an ASBR. All right, but very important concept. Because it is a special area type, external LSAs are not going to be allowed. So these type 5s are blocked. Type 3s will still be able to come in. Those are permitted, even though it's not on the diagram here. And of course, you'll have your 1s and 2s in here. But type 3s are blocked, and you'll have a default route as well to get to those external type 5s that you may want to get to. Because this is a special area type and type 5s are not allowed, the ASBR is going to be sending in those external routes as type 7s, which actually look exactly like type 5s. They're formatted basically exactly the same. And in fact, those type 7s become type 5s when they leave the area. All right? So kind of a lot of stuff happening here, but an NSSA is really just a stub area that allows those type 7s and allows you to attach an ASBR to that special area type. you can configure the area as NSSA even if it doesn't have an ASBR, because you may be anticipating that you're going to be adding an ASBR later on down the road. So you can kind of preface that by configuring that. Now, instead of having external routes, which are type 5s, we're going to have type 7s, which are represented as Ns in the database. N means not so stubby. So you might have an ON1 or an ON2 route based on the external route type, but the N indicates that it is a not so stubby area. It's interesting because the concept of understanding these route codes, right? O is a type 1, OIA is a type 3, OE is a type 5, and ON is a type 7. You can look at a routing table and you can kind of infer how that router is configured. I'll show you guys that when we get into the discovery a little bit later on. All right. The last special area type is totally NSSA. All right. Totally NSSA, just like totally stubby. Okay. So type 3s, type 4s, type 5s would not be allowed, as you can see from area 0, and a default route would be sent in. We would still be able to have an ASBR, which would generate those external routes as type 7s, which would then get converted to type 5s going into area 0. All right. All right. This is also a Cisco proprietary feature. All right. So the next thing that we're going to do is we're going to jump into our discovery for these concepts. And of course, we're going to explore in more detail all of these theoretical concepts by looking at them in the configuration, taking a look at how they look, and I'll show you lots and lots of interesting things as we go through the actual implementation. All right, so we're going to jump into discovery number 8. In discovery 8, we're going to look at some optimization of OSPF by the configuration of OSPF special area types, specifically stub areas. I'll probably demonstrate some of the other options as well. And also, we're going to take a look at summarization on our ABRs as well as our ASBRs, right? And specifically, we're running OSPF v3 in this particular environment. So OSPF v3, again, is slightly different than your classic OSPF, but overall, the configuration concepts are going to be the same. We shouldn't see anything too different in this particular case. So we're going to learn how to implement all 4 special area types, stub, totally stubby, NSSA, and totally NSSA. The stub and totally stubby areas are going to be deployed in this particular case to basically shrink the size of the OSPF database and in turn shrink the size of our routing table. Remember, as we talked about in our lecture, the stub area does not accept external routes, but it still allows type 3s, while the totally stubby area does not accept any routes and only a default route. The NSSA allows for the redistribution, but it still does not accept type 5s. We're going to see those type 7s, and we'll see this in the discovery as we go through our analysis of the database and everything. Totally NSSA, again, allows redistribution but does not allow anything to come into the area. No type 3s, no type 5s coming into the area. All right, we're also going to take a look in this discovery about how to configure default routing, what types of things can we do to manipulate default routing, how to implement route summarization on our ABR. We're going to summarize external networks as well on our ASBR. And again, we're going to see the impact that this has on our overall topology, our database, and so on. We have access to routers 1 through 4. The routers are all pre-configured with their address family configurations. We're going to take a look at first what is stub and totally stubby. We're going to implement default routing. We're going to take a look at more totally stubby configurations. This should say NSSA, not BSSA, but we're going to take a look at not so stubby and totally not so stubby, and we're also going to look at configuring route summarization here. Okay? So this is ultimately what our goal is. Area 0 can never be configured as a special area type. Area 0 always has to remain as a normal area. Area 1, we're going to go ahead and set up initially as a stub, and then we're going to convert it to totally stubby. And because Area 2 has an ASBR, we're going to focus on making that an NSSA initially, and then make it totally not so stubby after that. All right, that's our goal here. And we're going to be doing some summarization for these prefixes on our router 3, which is our ASBR, and most likely we're going to be summarizing some other prefixes on router 1 as well. All right, we've got a bunch of loopbacks on router 3. I'm trying to see if we have a bunch of loopbacks on router 2. It doesn't appear as though we do. But again, I will be more than happy to continue to demonstrate some of these concepts beyond the scope of the discovery, just so you guys can get a better grasp of everything. So the first thing we want to do is go into router 2. Remember, router 2 is the standalone router in area 1. And we're going to go in and take a look at what the database looks like, or the routing table looks like, for router 2. All right? Now, this is an interesting thing because there's a couple of things you can take away from looking at this routing table. I know for a fact that router 2 is in a normal area. How do I know that for a fact? Because I have external routes, right? Any special area type, it doesn't matter what kind, will never have E routes. Totally stubby, stub, not so stubby, totally not so stubby. You would never see external routes, at least not traditional external routes. Additionally, special area types, with the exception of one, all the other special area types will have a default route automatically configured. So because we don't have a default route here, and in combination with the fact that we have external routes, it doesn't appear as though this area is presently configured as a special area type. All right. Now, if I look at the V6 routing table, it will pretty much look the same. We have our external routes here. We also don't have a gateway of last resort. There's no default route listed in the routing table, so we don't have a default route in this case for IPv6 either. All right. So the external routes are being redistributed into OSPF by R4 and R3. They both act as ASBRs. R3 is advertising the 1055/16 and 5 of the 55XX subnets for IPv6. R4 is advertising the 198.51.100 network and the 198.51 : V6 network. Area 0 is our backbone. The backbone is the center of our network. And again, the backbone can never be configured as a special area type. It always has to be a normal area. Area 1 is a non-backbone area. We see the type 5s coming in. By default, this area accepts all of, being that it's a normal area type, it's going to accept all of the LSAs. So we should see type 1s, type 2s, type 3s, type 4s, type 5s, and so on. All right? So the first step in configuring stub configurations, the first thing to know about it is if I am going to configure an area, if I'm going to create a special area type, one of the major restrictions, if you will, or at least one of the prerequisites or requirements, is that all of the routers in the area have to be have the same configuration. So one of the, like I said, one of the requirements in order for an area to become, well, we make a whole area a stub. We don't just make a router a stub like in EIGRP. So if R1 is going to be configured as a stub in that area, then all the other routers in the area also have to be configured as a stub. In fact, if one router is marked as a stub and the other router is not, you will actually lose your adjacency. You won't even be able to form an adjacency in that case. All right, so they have us in this particular case we're going to go ahead and set router 1 as a stub. And let's go into router 1, config T. All right. And we're going to do this under address family. Notice when we actually specify the stub command, it's relevant to the area. So we're saying, okay, for area 1, this router is going to be a stub router. And we're going to do this for both v4 and v6. Notice as soon as I did that, I lost my adjacency with router 2. So I need to do the same thing on router 2. Config T, router OSPF v3, 1, address family IPv4, unicast, area 1 stub, and IPv4 or IPv6 unicast, area 1 stub. And you'll notice I got my adjacencies back. Now, if I look at the routing table, show IP route OSP, well, let's just show IP route. Look what happened to the routing table. All the external routes are gone. We're not getting those type 5s anymore. Also notice automatically, or automagically, we got a default route. I didn't set that default route. We didn't have a default route before, but by making the area a stub area, the ABR is generating that default route. If I go to the ABR and I do show IP OSPF, or yeah, show IP OSPF, show OSPF v3 database, self-originate, you'll see that this router is now generating, where is my, for area 1, I should see that the router is generating that OIA default route right here. For area 1, it's generating that OIA default route. That's the IPv6 one. And then for IPv4, we would see it as well. Let me find the IPv4, which is right here. This is the default route for IPv4. I did the self-originate command, so I know that router 1 is the one that's originating that default route. Does that make sense? So the configuration is actually really simple, isn't it? You just make all the routers in the area a stub. Once all the routers are a stub, then you don't have to worry about anything else. Everything else pretty much happens automatically. Right? We have now configured area 1 as a stub area, which means that R1 is sending in the default route, R2 is getting that default route and utilizing that default route for reaching those external prefixes. So we didn't lose connectivity. We still have connectivity. All right? We just reduced the size of our database. So they didn't had us to do this again on router 2, which I already did. And then they had us investigate the routing table on router 2 and take a look at the routing table on for IPv6 as well. The key here is that default route is coming in as an inter-area route. It's coming in as a type 3 because it's being generated by the ABR. ABRs generate type 3s, don't they? All right. I still can't ping the internet. So if I go back to my router 2 and I try to ping the host on the internet, I get unreachable. But it's at least leaving the area. I know it's leaving the area because I have a default route that points to the ABR. The issue here is not that we can't get to the internet, it's that there's a default route missing somewhere else. There's a default route missing in the backbone. If I try to ping the external network to router 4, I can ping that external network just fine. Looking at the topology diagram, this router 4 has got this external connection to the internet. And the reason why we can get to that specific network is because router 1 actually has a route. Which brings us to our next step, right? We have a default route to leave the area, but R1, if you go to R1 and you do a show IP route, you'll see that R1 does not have a default route. So the ABR is generating a default route into OSPF, into area 1, but R1 itself doesn't have a default route. You see what I'm saying? So I'm assuming that one of our next steps here is to go ahead and generate default information originate. They do a couple of other pings here on router 2. Of course, we know that what's going to happen because whatever applies to IPv6 is, or whatever applies to IPv4 is going to apply to IPv6. All right. So routing from the stub area is fine. We've got a default route to leave the stub area, but we don't have a way to reach the rest of the network. So this is where we want to implement our default routing. Now router 4, if you look at the topology, router 4 is the router that goes to the internet. So my first inclination would be to verify whether or not router 4 actually has a default route itself. Router 4 should have a default route. So let's go into router 4 and let's do a show IP route. And sure enough, router 4 does have a default route. It points to 100.2. Show IPv6 route. Oops. And it also has a v6 default route that points to the external. Why is it important for me to verify that? If I originate a default route, I want to make sure I have a default route myself to make it work, right? I could do the default information originate always. Maybe I don't have a default route, so the packet will get to me, but then it will fail. All right? Because we do have a default route, we should be able to go do it work just fine. We're going to go into our OSPF process. We're on router 4 now. Config T, OSPF v3, address family IPv4, unicast, default information, default dash information, originate. Now I'm going to do something a little bit different than what the book does. You guys can do whatever in the book if you want, but I'm going to say metric type just to demonstrate that I'm going to send it in as an OE1 as opposed to an OE2. In our case, it doesn't really matter if we do that. We don't gain anything by sending it in as an OE1. I just want to show you that how it will change in the output of the routing tables. So now if I go to router 1 and I look at the routing table, there is my default route. Mine comes in as an OE1. Yours probably comes in as an OE2. Your seed metric is 1. Yes? My seed metric is 11. Well, my metric is 11 because I'm counting the cost of the link on top of the initial seed metric. So easy to inject the default route using OSPF. You don't have to do redistribution, but it does come in as an external route, which means it would not be allowed normally into our special area types, but we don't care about that, do we? Because the special area type already has a default route that was generated by the ABR. Does that make sense? So we're kind of incorporating all these different building blocks now, and hopefully by the time all this is done, you have all the pieces necessary to build the entire enterprise, right? We talked about just doing basic peering relationships, how the peering relationships established, exchanging the link state advertisements, building the database. Now we're talking about building a multi-area design and then adding optimization to that design. All right. This was after. Of course, your guys' shows up as an OE2. Mine shows up as an OE1. Also V6, OE2. If I look at the database on router 1, show OSPF v3 database, what they're trying to demonstrate in this output here is they're just trying to show you that you're getting that type 5. Specifically, they're looking for these type 5s. There's the default type 5 from router 4 and in IPv6, and there's the default IPv4 default route from router 4. You have to kind of scroll through. There's a lot of information in this output, so you kind of have to scroll up to see it. All right? All right. Now if we do our ping to that external network, the ping should work. Unreachable. No! That's probably just a misconfiguration. 021 should be on router 4. Let me see. Show IP route. You know what? That's probably because it's missing on the internet router. One of the things that I was missing when I was establishing the configuration here was the config for the internet router, so I had to kind of guess. Show IP interface brief. So I'm assuming that we needed to, on the loopback, you guys don't have, you get the idea, it's going to work. I'm going to, well, I won't make the change. Well, I guess I'll make the change right now. Most likely they had that address defined on a loopback here, just to test with. So now if I ping from router 1, it should work. Yeah. So basically I just didn't configure it on there. Same thing with the V6 address. Copy that. I will fix this topology and save it, upload it again. So if you ever go back to the lab later on, I know you guys are just dying to do that every day. IPv6 address. /64. Oops, not double colon. I already have the double colon. All right. So I should be able to ping that now as well. Okay. I would not have been able to ping that before though, because I didn't have any route to those destinations previously. All right. So pretty much now on the ABR, we can see that we have those default routes. The asterisk in the routing table indicates that it's a default route. They're talking about specifically when you do a show IP route. Anytime you see an asterisk next to a route, that indicates that that's the default route. That's the actual route that's being used as the default. We can see it up here, candidate default. So that would always, that's not specific to OSPF, that's actually any routing protocol. So we can now reach those external networks because the default route exists on router 1. Router 2 can reach those external networks because of 2 different default routes. So if I go to router 2 and do the ping now, it goes through, but this is a recursive default routing process, right? Because I'm getting the default route from the ABR, I'm using that default route to get to the ABR, and then the ABR has its own default route that it was learning through default information originate. So all I did is added a loopback interface on the external, the internet router, and just put those 2 addresses on that loopback. All right. What about totally stubby? Again, what does totally stubby allow in? Nothing. Except Well, 1s and 2s are already inside. What is sent into the area by the ABR? Default route, that's right. To change an area from stub to totally stubby, all you have to do is go to the ABR and add the keyword no-summary. That actually kind of makes sense, doesn't it? Because what are we further filtering? What are we filtering on top of the externals? Summaries. We're saying no summaries, bro. You're not allowed to have any summaries. All right, so let's go to do that on router 1. By the way, you only need to do that on the ABR. You can leave the stub configuration on the other routers internal the same. Router OSPF v3, 1, address family IPv4 unicast, area 1 stub no summary, and v6 unicast, area 1 stub no summary. Let me show you something because I think this is important. I'm going to do a quick packet capture here. Nothing really changed from router 2's perspective as far as the configuration. Router 1 is really now being instructed to say, hey, you're not allowed to let anything into this area. No type 3s, no type 5s, no type 4s. You can still send out type 3s to the other areas, but you're not allowed to let any type 3s come in. So if I'm looking at this hello packet, remember we're not seeing any v4 information here because we're running OSPF v3. OSPF v3 uses v6 as the transport for both v4 and v6 information. What I wanted to specifically show you, though, was this right here. Where is it at? Not sure where that dang stub flag is, but watch what happens if I make R2 not a stub, right? If I just put R2 back in the area as not a stub. So router OSPF v3.1, address family IPv4 unicast, no area 1 stub, and v6. I lose my adjacency, no area 1 stub. All right, and I lose my adjacency. Now do a debug, OSPF v3. Let me do this. Debug OSPF v3 adjacencies. Let's see if we get a notification that tells us that we can't form an adjacency because of the stub configuration. Let me do events also. I'm receiving hello packets from router 1. Router 1, somewhere in that hello packet is marking that stub flag. I don't know where the heck it is. This is coming from router 2. Router 2's packet should look normal, but the one from router 1, let me check the link local address on router 1. Show IPv6. Now let me do, interface. And it looks like this one is FE80:1. Which one is the one that, Ethernet 1.1 is the one that goes over there. So we're looking actually for this one right here. This is router 1. So I don't see it here. The R bit and the V6 bit are the only 2 bits that are set. So if I compare that to what's coming from router 2, the R bit is set, the AF bit is set, E bit is set. This has got to be it right here. It's got to be the E bit. So the E bit says if that E bit is turned on, it says I'm allowed to have external routes. If the E bit is turned off, it says I am not allowed to have external routes. Does that make sense? So it is, they call it the stub flag, but it's not, hey, I'm a stub. It's, hey, I'm not allowed to have external routes. So because this E bit is turned on and the E bit is turned off on router 1, we're no longer allowed to form an adjacency. External is not allowed, whereas external is allowed on router 2. That's got to be it. That's got to be the bit that gets marked to indicate the stub configuration. So if I go back here and I make this guy a stub again, that E bit should be turned off at that point. Address family, IPv4, unicast, area 1 stub, and IPv6 unicast, area 1 stub. Undebug all. There you go. So now if I go back to my Wireshark, coming from router 2, I should now see that E bit turned off. And let's get right here. Hello packet. Yep, the E bit is turned off. All right. So we finally found it. That is the bit that we would have to look for to see if we were going to be able to form an adjacency. Now we did the no summary on router 1, so guess what a routing table in router 2 is going to look like? Show IP route, no routes at all from OSPF. Only the default route. So no OIA routes except for the default. That's kind of interesting, right? Because when you do a no summary, you're not supposed to see type 3s, even though technically the default route is a type 3. It's OIA, but again, it's being generated by the ABR into that area only. You could see where this could benefit you quite a bit. If you only have a single way of leaving the area, why send in thousands of routes when they're not necessary? Right? That's kind of the whole point. So just by adding the no summary keyword on the border router, we're now not allowing type 3s in. Okay? So the only OSPF route we see is the default route that's being automatically injected. Of course, we should still be able to ping because we didn't change reachability to the external networks. We still have the default route. I'm not going to ping the rest of those, but. All right. So the leaf router, in this case router 2, we have spine and leaf design. The spine is the backbone. The leaves are the non-backbone areas. The leaf router is now in a totally stubby area. It's going to have the smallest possible routing table. Connected in local routes plus a default route from the ABR. So no type 3s allowed in, no type 5s allowed in. Notice that when we're configuring this for V4 and V6, it's pretty much the same, isn't it? It hasn't changed. V4 and V6 are configured the same way. All right. What if I had multiple ABRs? What if I had, let's say I had a situation where I had, say for example, this area here, and here's an area, and I have an ABR here, and this is configured as a totally stubby area. We know we're sending in a default route. But then I have another ABR connected. It's also sending in a default route. Now, by default, if you look at router 2, the metric, it comes in as an IA route, which means it's not external. So the metric is going to be reflective of essentially the cost for me to get to the ABR. Notice the default route is coming in as with a metric of 1. I know it's coming in with a metric of 1 because there's an Ethernet link between router 1 and router 2. That's going to have a cost of 10. So the total path cost is 11. So in my, going back to this scenario here, what if I said, you know what, I want to prefer this router for all the default traffic, and I only want to use this as a backup. I probably want to change the metrics that are used to send in that summary or that default route. And that's what they're talking about in the next section here. They're saying area ID, default cost, cost value. So I can come into my database here. Let me see if they actually have us change it. They do not. So I'm going to go ahead and change it as a demonstration here. We only have one ABR in our case, so it wasn't really necessary to change it. But let's go to my router 1 and router OSPF v3 1 and address family IPv4 unicast and area 1 default cost 100. Now when I go to router 2, oops, you can see the metric changed. So if I have two ABRs sending in a default route, I can make one higher than the other one just to force everybody to leave the network from that ABR. I could leave it to the default and just let the normal metrics make a decision. Some routers might choose one, some routers might choose another, but I may want to control that and control who actually routes the default traffic out of the area. So our totally stubby database, obviously on router 2, we should only see type 1s, type 2s, type 8s, type 9s. Well, maybe one type 3. Here's our type 1s. Here's our type 2s. Here's our type 3. It's kind of counterintuitive, right? Because we say, well, it's a totally stubby area, so it shouldn't have type 3s. The exception to that rule is the default route. And this is the default route. And of course, we're going to see our types 8s and 9s. 8s and 9s would exist regardless because those are inside the area. Right? There's our 8s and there's our 9s. 8s are the link locals. 9s, excuse me, are the prefixes that are tied to our type 1s. All right. Much simpler database. Yeah, simple to who, right? It's definitely a lot less information. And you also have to keep in mind, we're doing this in a very confined space, right? We only have a couple of routers. But if you have a full enterprise network, you could have thousands of networks, thousands of prefixes. So you could definitely see the benefit if you have a whole bunch of networks. All right. Task 4. NSSA and totally NSSA. So again, in our topology, we have router 3, which is basically redistributing external routes into OSPF. So this is an ASBR. Right now it's connected to a normal area. Area 2 is configured as a normal area. But if I want to convert area 2 to a special area type, watch what happens if I try to make area 2 a stub. So I go into, let me go back to my v4 address family, and I say area 2 stub. All right. It reset the adjacency, which we would expect because I didn't configure R3 as a stub router. But what if I try to go to router 3 and configure it as a stub? Router OSPF v3, address family IPv4, unicast area 2 stub. It should start giving me errors saying you're not allowed to be a stub because you're an ASBR. This area is not allowed to be a stub. I'm not sure why I'm not seeing those errors. I should be. Do show IP OSPF v3, show OSPF v3 database, self-originate. Show OSPF. I should be getting errors. Let me see. Show OSPF v3 database self-originate. Sending them in as type 5. Normally what would happen, it's clearly ignoring the stub configuration. Did I do the right area? It is area 2. You know what? Because it is OSPF v3, I might have to do it for the v6 address family. Let's do that. Let me do the v6 address family. Because what it should be saying is it should be giving me an error saying you're not allowed to configure this area as a stub because it has an ASBR. So area 2 stub. And let me do the same thing on router 3. Address family IPv6 unicast area 2 stub. I know I've seen it throw that message before. No, it's allowing the adjacency to form. It's interesting. In the past when I've done this, it's told me before, you're not allowed to do that. This is an area with an external router. Let me see if I'm getting those external routes on router 4. I'm not getting the external routes anymore. I don't see any type 5s. Show OSPF v3 database. I'm getting the type 5s that I'm originating into area 0, but I'm not getting any type 5s. So it is technically broken. I don't know why it's not giving me the messages telling me why it's broken. But let me see if I see the type 5s on router 1. Show IP, show OSPF v3 database. Yeah, see, I'm not even seeing the type 5s in area 2. So it did break it. I'm getting the type 5s from router 4, but I'm no longer getting the type 5s from router 3. I'm just curious why it didn't give me a warning. Usually I see a warning that says, hey, you can't do that. There's an ASBR. All right, so let me get rid of that config. Address family, IPv4. I wonder if it would do that in classic mode. I know I've seen it. I'm going to say that it would probably give me the warning in classic mode, but for some reason it's not giving me the warning in address family mode. But that's okay. We know it's not working because I lost my external routes. Let me go back to router 3 and do the same thing. No area 2 stub. v6. No area 2 stub. Now if I go to router 4, I should see those external prefixes coming from router 3. Yeah, so they're back now. So we know for a fact that it broke it. And maybe it just said, you know what? I'm just going to filter out the type 5s because you made me a stub area, and stub areas are not allowed to have type 5s. Right? Which makes sense. Stub areas are not allowed to have type 5s, so even though router 3 is trying to throw in type 5s, it's just going to say, nope, can't do it. Can't put those type 5s in. But what if I do want to have those type 5s? I need to set up the not so stubby. All right? Now, if you recall, a not so stubby area allows you to have an ASBR. It allows those external networks to come in as type 7s, and then they would get converted to type 5s when they leave the area. We still don't allow type 5s in. No special area type is going to allow type 5s in. Area 1 is configured as not so stubby, which is equivalent to stub, which means type 3s are allowed in, and totally not so stubby, nothing is allowed in, only a default route. It's interesting about the concept of the not so stubby. That's kind of an interesting concept. I'm going to show you something about that in a minute. All right. They go into a discussion about the metrics E1 versus E2 and N1 versus N2. We'll see that a little bit later on. But to configure this as a not so stubby area, first thing they want to see is what kind of routes do I see on router 3? And by the way, router 3 should pretty much see different types of routes. Well, it's getting a default route. It is getting the default route. This is not the default route that's generated from the stub configuration, because I don't have a stub configuration. This is the default route that's being generated by default information originate. Mine's an E1 because I changed it. Yours is an E2, but it is still an external route. So I know that this is not a special area because it has external routes. Can't be a special area. How do I make it not so stubby? You go to the border router, area border router, go into your OSPF process. Let me just find the page here because I want to make sure you guys are on the same page here. They're just verifying the routing tables there. And instead of using the keyword stub, we use NSSA. All right? Just make it a not so stubby area. So I'm in address family for v4, area to NSSA, and v6, area to NSSA. I lost my adjacency because, again, I now have that flag, and we'll look at the Wireshark capture and see if that E bit is turned off again. It should be, but then we should also see another bit turned on. Let me go to router 3, address family v4, area to NSSA, and v6, area to NSSA. Now look what happens if I do a show OSPF v3 database self-originate. All right. I should see the type 5s go away. Yep. Type 5s went away. They became type 7s. I did it kind of quickly, but if I scroll up, this was in the process of the area reconfiguring itself. 1, 2, 3, 4, 5 different external prefixes, and they became type 7s. 1, 2, 3, 4, 5 external prefixes. How do they look on router 4? They look like type 5s. Because again, the type 7s are allowed in the area, but when the type 7s leave the area, they become type 5s. So let me do the Wireshark capture on that link. Oops, didn't want that. Try this again. Stop. Stop it. Stop the capture there. Let me do the capture here. Because what I want to see is what flags are set now that this is an NSSA. Is there a different flag that's set in the hello packet to indicate that I'm in an NSSA? Because type 7s are allowed now. Well, type 7s are technically external. Type 7s are technically external routes. So this is from router 3. Oops. And let's see, options, N bit. Yep, N is NSSA. That makes more sense, right, as opposed to E. So type 5s are still not allowed, but because it's marked as N, not so stubby, we know type 7s are allowed. All right. But let's look at one other thing on router 3, show IP route. This is very strange. I don't know why Cisco decided to do this. This wasn't defined as part of the RFC for OSPF, but we are missing something, aren't we? Gateway of last resort is not set. For stub and totally stubby and totally not so stubby, the ABR generates a default route. For not so stubby, it doesn't generate a default route. Don't ask me why. I'm sure there's a wonderful reason. I'm sure people know what that reason is. I haven't researched it. There's probably some logic to not putting in a default route if it's an NSSA, but putting in a default route if it's totally NSSA. Maybe perhaps it has to do with the fact that we have an ASBR. Maybe we're reaching those external networks through the ASBR. I don't know. But right now, I can't get to those external networks. I can't ping those external networks because I don't have a default route. And I'm sure they're going to mention that here. By the way, so the stub flag, stub area flag, hey, they do mention it in the book. The EBIT is the stub area flag. That's not set anymore. It's, well, set to 0. All right. We do have our OIA routes. We do not have a gateway of last resort. So our pings are going to fail to the external networks. R3 has lost its V4 and V6 default routes and the Type 5 external LSAs for the internet. The NSSA is the only non-regular type of area into which a default route is not advertised automatically. I can use this command, area ID, NSSA default information originate, to override that behavior. So I would do that on my area border router. And I would say area to NSSA default information originate, and for V6 as well. Now if I go to router 3, it will have a default route. Notice it's coming in as N, O-N, which is kind of strange again because we're not supposed to allow external routes, but it's coming in as a type 7, and type 7s are allowed into the not so stubby area. All right. Oh, they did have us do that. Step 5. Show IP route, we can now see that we have a gateway of last resort coming in as a type 7. And that's what we see here as well. We should actually see one more there on the database for router 3. It's missing from the book, but oh, it's up here. Is it at the top in the book? Did I just miss it? I did. It's right there. For some reason I was looking for it at the end. I don't know why. Because the advertising router is 1 instead of 3, it's going to go first in the list. And our pings will work. All right. What if I want to set the metric for the default route? Same concept. At the end of the default information originate command, I can specify metric. I can also specify metric type. Right? If I go back to router 1 here and use the question mark, I can say what is the metric, what is the metric type, and no summary is, that's related to NSSA. What do you think NSSA no summary means? If I do that on the ABR, NSSA no summary. Totally NSSA. Type 3s are not allowed. Right now, type 3s are allowed. No summary means no type 3s. That's how we make the area total NSSA. All right. Or we could do NSSA only. Basically say only send in the default route. But we're not going to do that in this case. They're just showing us the type 7 on the other router in this case. Router 1 has the type 7. And it's getting the type 5s, by the way, from the other areas. if I look at the database on router 4, I see I'm getting those external routes. They're coming in as external 2, meaning type 5's metric type 2. What if I wanted to change that behavior, by the way? If I wanted to change that behavior, it's a little bit more challenging, because if I do a show run section OSPF, those routes are coming in because we're doing a redistribute connected. So what if I did this? Router OSPF v31, address family v4 unicast, redistribute connected. Do I have an option to change the metric or the metric type? I do. So this is where I would, and the redistribution process is where I would change them from, say, an N1 or an N2 or an E1 or E2, and I would set the seed metric. So I could say metric 1000, metric type 1. Now when I go to router 4, I see those routes. They're coming in as E1 now, and that's the metric now, is 1000 plus the cost of the metric of the links in between, or the cost of the links in between. All right. And we can do some pings. They're just verifying reachability. All right. So they want us to basically take out the default information originate, because we're going to convert the area to totally NSSA. So I'm going to go back to router 1, and I'm going to take out the default information originate. We don't need it, because if I do area to NSSA no summary, all right, look what gets injected into the routing table. A default route. Remember, the only special area type that doesn't automatically generate a default route on the ABR is NSSA. Every other, all the other 3 special area types generate a default route into the area. All right. Total NSSA, just add the no summary keyword. They want you to remove this. You actually technically don't need to remove the default information originate. You could leave it in there and still do no summary. It would still work. But there's really no need to have the default information originate anymore, because it wouldn't inject the type 7 route anyway. It's going to come in as an OIA route. OIA route here for V4, or an OI route for V6. Pings still work. No problem. All right. All right, so the next task that we're going to look at in this is to do our summarization. Something we've already seen multiple times, obviously, in the Encore class, and I just demonstrated it in our last discovery as well, using the area range command on the ABR to do our summarization, or using the summary address or summary prefix command on our ASBR. So in OSPF v2, we would typically use the area range. And again, the area ID that you specify is the area from which the summaries are coming, not to where, not the destination area where the summaries are going to be sent to. So we always summarize from the area. We don't summarize into a particular area. There are ways, by the way, to filter out what areas the summaries would go into. So for example, if I'm summarizing on an ABR and that ABR happens to be a member of multiple areas, there are other ways to say, okay, I only want those summaries to go into the backbone, or I only want those summaries to go into area 2 or whatever. But we don't really discuss that in this class here. That's something I typically talk about in the CCIE enterprise class. By the way, if you're interested, guys, on our YouTube channel, and I'll be posting some more tonight. I usually post them every week. The CCIE enterprise videos, which are deep dive discussions into all the stuff that we're talking about. So those are pretty interesting. And all those labs on that, in that lecture series are also recorded using the GNS3 labs. So you can actually build those labs and kind of play around with them yourself. Anyway, we're going to take a look at summarization. If I look at Router 1's database, we want to see what kind of routes we're going to be summarizing on Router 1. Oops. Do a do, not a no. There we go. And it looks like we've got these external routes here, 5564.0, 5564.128, 5565, and 55.127. So if I were to summarize those, probably well, there's really only a block of 64 is the best I can do in that case, right? Because I have to technically in the third octet go from 64 to 127. So a block of 64 would be a 192 in the third octet, which would be a /18. So I could summarize these /25s and /24s down to a /18, unless I decided to just summarize the 64s together and leave the other ones by themselves. But the idea here is that we do want to create a summary. Again, only 4 networks going down to 1. That's not going to save us a whole lot. But this is just for the purposes of demonstration, not for the purpose of actually reducing the size of the routing table. All right, so those are the prefixes that we're trying to send into the domain as summarized. They show up as N2 in the lab because I changed mine to N1 just to demonstrate. Same thing with the V6 routes. If I look at the V6 routes on Router 1, do show IPv6 route. It's the 5501, 5502, 5511, 5512, 551F. So this summary is pretty straightforward. I do a 2001 DB8055.1 with a double colon slash, that would be a 60, a /60, because basically I'm just not including the last 4 bits. So I've got the first hextet, which is 16 bits. The second hextet is another 16 bits, which gets me to 32. The third hextet is another 16 bits, which gets me to 48. And I'm summarizing the first 3 hexadecimal characters in the last hextet, which means I only have 1 hex character left, which is 4 bits. So 64 minus 4 is 60. So I'd be summarizing down to a double colon /60 in that particular case. All right. Now, if I also wanted to include 01 and 02, then I have to summarize basically down to 59, right? Because the 0000 and the 0001 means that the last bit in the third nibble of the last hextet would be one that could change. Did you catch that? The last bit in the third hextet of the third nibble. Third nibbles are 4 bits. That's what we actually describe a hexadecimal character as. Everybody does agree that the summary would include at least that, right? 2001 DB8055, right? This hextet, or this hexadecimal character 00111 means that actually we have a 51. This one we would probably leave by itself because then we're starting to get into the whole hextet there. But so the difference between 0 and 1 is the last bit of that nibble. So it would we'd go to a 55 double colon /59 in that case, not a 60. We'll see what they did in the book If they did something different in the book, then I'll go ahead and put it in Notepad. You know, let me do it anyway. I want you guys to understand, even though the purpose of this discussion is not to learn how to calculate summaries, the purpose of the discussion is learn how to implement summarization, but everybody agrees the summary should be at least this. I think that's pretty straightforward, right? And then we have a 0, 1, we have a 0, 2, we have a 1, 1, a 1, 2, and a 1F. So we also know that it's really this hex character that's unique. This is 0, 0, 0, 0, 0, 0, 0, 1. This is 0, 0, 0, 0, 0, 0, 1, 0. This is 0, 0, 0, 1, 0, 0, 0, 1. And this is 0, 0, 0, 1, 0, 0, 1, 0. And this one is 0, 0, 1, 1, 1, 1, 1. So when I said we're going down to the last nibble of the last bit of the third nibble in the fourth hextet, I meant this bit right here. So this becomes my summarization boundary. And if I subtract from 64, 63, 62, 61, 60, 59, meaning that 59 bits of the address are the same for all of them. That make sense? So that's technically what we should summarize down to. Now that would actually go from 0, 1 to 1F. Actually 0, 0 to 1F. Actually, technically that summary /59 would include 2001 DB8 :0 :55 double colon all the way to 2001 DB8 :0 :55 :1F. That's what the summary range would include. All right. We'll see what they did in the book, but that's really what it should be calculated as. So as far as the actual configuration, yep, that's exactly what they did. They made a mistake again, though. Not a good mistake to make. They changed the meaning of that fourth hextet. Is that a mistake? No, that's actually correct. That is actually correct. I put, in mine, I put 55 double colon, but actually that's not correct. Because if I write 55 double colon, that means that the zeros are before the 55. We need to make sure that we know that the zeros are after the 55. Right? That's really important to understand because the 55s, there's no zeros in front of the 55s here. So that's actually a pretty important point. If I had just done 55 double colon, it would have assumed that the zeros were in front of the 55. Actually, that summary wouldn't have worked at all because the 55 would have been converted to something else. But let's go ahead and put it in. Router OSPF v3 on router 3. And we're just going to put in our summary prefix. So address family v4, unicast, and we'll put in our summary prefix. Interesting. They're doing a 64/18. Yeah, that's the one we calculated for the v4. 64/18. Remember why we have the 64/18. If I go back to, of course, I'm doing it in the wrong router again. I didn't finish it this time, so that's good. But the 64/18 is based on these routes here. Remember 64.0, 64.1, 28, 65, and 127? I would be summarizing in the third octet, but it has to include a block of 64, which is what gets us to the /18, because 192 minus 60, or 256 minus 192 is 64 in the third octet. So a 255.255.192.0 ends up being /18. But I do need to make sure I'm in the right router. So we'll do our summary here. Summary prefix. And address family IPv6 unicast. And we'll do our summary prefix here for IPv6. Remember, these are routes that are being originated by the ASBR. We use the area range command for routes generated by an ABR. All right. And if I go back to router 1 and I do a show OSPF v3 database, I should now see those type 7s in area 2. Let's see. They're coming from router 3. So I should see the type 7s. It is a not so stubby area. Yep, here it is right here. There's the /59. The type 5s are coming from other areas. Remember, router 1 is in multiple areas here, so it's a little bit confusing when you're looking at the output here, but we're definitely looking for the type 7s because it's coming from area 2, which is right here. As the /59. Notice we still have the 64s. Why do I still have the 64s though? Something isn't right. I shouldn't have the 64s anymore. I probably just didn't give it enough time. Let me see. Yep. There's the type 5s are gone. And yeah, I just didn't give it enough time. So the 64s should be gone. What would I be able to determine if for some reason some of those individual prefixes still existed over time? It would mean that my summary wasn't calculated correctly and those prefixes just wouldn't be included. So there's my /59. And then in IPv4, I should also see that /18. And let's see. That's the type 5s. Where's my type 7s? Now this is interesting. I am not seeing my /18. So it doesn't appear as though my /18 went in correctly. Let me go back. I might have been in the wrong address family because I didn't really change my mode. I just assumed I was in the right mode. Yep, my v4 address family is missing the summary because I was probably in v6 address family mode when I put in the command. It's kind of interesting it didn't give me an error. Like say you can't do a v4 prefix in a v6 unicast mode. But now I should see that. And let's just do an include /18. Should show up. Why is it not showing up? OSPF v3 database. Still not seeing my /18. It should be coming from router 3. Oh, because I've copied the completely wrong address. I'm not seeing a /18 because I didn't put in a /18. Sorry guys, I thought I had copied the right address, so let's do that. It would help if you actually put in the right prefix. It's been a long day. Been a long week. Not that I'm not happy to have you all here. Yeah, maybe not Scott, but no. There's my /18, and eventually the other ones will go away, and all I'll see is the /18. All right? It's kind of funny because I'm still seeing that /24, but that's because I put that in. If I go back to router 3, I'd have to take that out, because remember, you can have more than one summary section router. So I'm actually sending in 2 summaries, 18 and 24, so I would just have to take out that other one real quick. which, by the way, is kind of interesting because you could say, you know what? I want to send in the 18, but I still want the 127 to show up by itself. And by putting in the 127 with the /24 prefix, I'm generating that summary, which overrides the global or the longer or the shorter match prefix and injects both routes. So there's all kinds of ways that you can kind of influence how the routes show up in the routing table. In my CCIE class, I really get into that a lot because we do a lot of what we call traffic engineering in OSPF, and the way we manipulate the traffic flows is by manipulating how the routes are injected into the OSPF database. All right, we stumbled through that, but we got through it. All they're demonstrating here is that that /18 route is now showing up. Also notice on router 3, we get the null 0 route. Remember, the null 0 route there is there for loop avoidance. If there's a particular prefix that's included in the summary range that I don't have a specific route to, I don't want to end up using a default route to route that packet, so I'm going to match that packet to the null 0 route to make sure the packet gets dropped and it doesn't inadvertently get looped around the network. All right? Very, very important. We would also see the null 0 route in IPv6. We didn't have to create that null 0 route. It was just created automatically because we did the summary. Preventing loops, that's the purpose of that null 0 route. On our router 1, we now see the /18. We see the /59 as well in IPv6. Notice it's coming in as an ON route because, again, this is a not-so-stubby area. It's actually a totally not-so-stubby area in this case. And those come in as N routes. Those are my type 7s, my type 7 LSAs. We look at the database on router 1, which is really what I was looking at to verify everything. Look at the database on router 1, and specifically I'm looking for those type 7s in area 2. There's the type 7, the /18 type 7 in area 2. Notice there's 2 of them. Where the heck did this default one come from? Well, guess what? We know where it came from because we see the advertising router. It came from the ABR because this is a totally NSSA. The ABR is injecting that default route automatically into the area, which is kind of interesting because in the stub and totally stubby, it didn't come in as external. In stub and totally stubby, it came in as OIA. But in totally NSSA, it comes in as an N route. I'm sure there's a reason why they decided to do it differently with not so stubby, but it doesn't come in as a type 3, it comes in as a type 7. Which, by the way, means that I should see that in my default route on router 3 as well. Do show IP route. Listed as an OIA here, that's interesting. Do show IPv6 route. It's also listed as, where's my default route here? I don't have one here. That's interesting. I don't have a default route for v6, which means most likely I forgot to apply the no summary command for the v6 address family. Let me check real quick. Yep. So it's kind of interesting if you recognize certain elements of the config, right? I just looked at router 3. For v4, I saw the NSSA. This is why it's coming in as a type 7, because I still have the default information originate. If I take this out, it should come in as a type 3. So let's fix all this. Config T. We don't need that default information originate anymore because it's a totally NSSA, which means it's going to generate a default route anyway. So I'm going to just do area 2
NSSA, no summary. And again, as I was saying, I looked at router 3 and I said, wait a minute, I don't have a gateway of last resort for IPv6. But I know that this is a stub area. In fact, I know it's a totally stubby area. It should be a totally stubby area. And if it's a totally stubby area, sorry, let me use the right term, total NSSA, because it has an ASBR. If it's a total NSSA, it should have a default route. The default route should be injected by the ABR. And so I said, you know what? I probably forgot the no summary command on the perimeter router. And sure enough, under the v6 address family, I forgot the NSSA no summary. So now if I go to router 3, I should have a default route, and it's coming in as OIA. So two things were happening there. Because I have the default information originate command on the border router for v4 address family, it was sending it in as a type 7, the default route. Now it's sending it in as a type 3, do show IP route. It should be sending it in as a type 3. Yep, it is. So I said, well, there must be a reason why they're doing that. There is no reason why they're doing that. The reason why they're doing that is because my configuration was messed up. I was sending it as a type 7 with that default information originate command. Remember, default information originate always generates an external route. Even if it's a normal area, it comes in as an external route. All right, so if I go back to router 3, and I look at the database, let's just exit out here. Show OSPF v3 database. I should now see only one type 7 for both v4 and v6. Yep, I'm only seeing one type 7, and I should see a type 3 for the default route. Inter-area prefix link states is type 3. I see that for the default route there, and I see it for the default route here. Inter-area prefix link states for area 2. So everything finally looks the way it should look. All right. Obviously the pings are going to work. We're getting a default route. The default route's being originated by the perimeter router, so we don't really have to do that. All right. And let's see, that's pretty much it for that discovery. We talked about this concept already, sending a default route in to a special area by injecting the cost. Area ID default cost. Why would I want to make this cost 1 perhaps and this cost 10? Because I want my default traffic to flow out of the top router. I want my default traffic to leave the area through ABR1, not ABR2. Otherwise, they both get inserted with the same metric, and then we simply use the metric to get to the ABR to determine which router we're actually going to go to. All right, so we'll wrap up this discovery. We're going to go into our authentication discussion, and then we'll do an authentication discussion.
Alrighty, now we're going to move on to the last two topics before we get into our next discovery. And in this next topic, we're going to talk about the default route cost in OSPF special areas. Now, when we get into our discussion of route manipulation, policy-based routing, that kind of thing, we're going to talk about how we can manipulate costs in lots of different ways for things like redistributed routes and applying route policies or policy routing policies to policy-based routing scenarios. But in this case, we are talking about setting up Area 1 as a stub, which, by the way, will automatically generate a default route. And you can see that first bullet point. By default route, that stub ABR is going to advertise that default route with a cost equal to 1. And we saw that actually in our discovery as well. And in this particular scenario, we actually have two ABRs, ABR1 and ABR2. Now, this route will be injected as a summary route, type 3 OIA route, being that this is a stub area. And as such, the cost of the links will be cumulative along with whatever the initial seed metric is for the cost of the default route. But we may want to influence that cost by artificially setting the cost of one of those default routes to a higher value than the other default route to influence which ABR we're going to use to leave the area. And that's essentially what we're seeing in this particular case. So for the secondary ABR, rather than having that default cost of 1 being sent in, we're going to go ahead and establish a seed metric or a seed cost of 10 for that particular default route. And we can use the area ID command to actually set that value. And this is a very specific use case scenario, obviously, because we are talking about having multiple ABRs. But there may be other reasons why we would set the cost of a default route. It wouldn't necessarily affect longest match routing principles that we would apply with normal routing in our global routing information base. Routers will always tend to choose the longest match route before they choose a shorter prefix. And of course, /0 is the shortest possible prefix that we can have. But this option gives us a little bit more flexibility on controlling how the traffic is going to leave the OSPF domain. We'll see this in the discovery as well when we get into our next discovery. Our final section before that, though, is our OSPF authentication section. We talked about this in EIGRP as well. We're going to run authentication on our devices to ensure that we have or we trust or understand that the peering relationships we have are trusted, that the neighbors that we've established adjacencies with are known and authenticated neighbors, and that all the messages that are coming from those peers are authenticated as well. Now, traditionally, when it comes to routing protocols, this was limited to authentication only, meaning that all of the message types, the hellos, the DBDs, the link state updates, link state requests, etc., would be sent in the clear. And we would simply attach some sort of hash value to those messages based on a secret key and the calculated hash based on a hashing algorithm to verify not only the integrity of those messages because of the hashing process, but also the authenticity of the source, not to an individual host, but to a host that shares a common shared secret key, which is incorporated into the hashing process. In OSPF v2, we actually have 2 different ways that we can implement authentication. We pretty much focus on one way, which is the message digest authentication method, because obviously that is going to be a more secure option than the other option, which is plain text authentication. Plain text authentication, the password is actually sent with the updates, and you would be able to see that authentication, those authentication credentials in a Wireshark capture. So clearly we're not going to try and utilize that particular method. In order to configure this classic mode authentication, we're going to enable OSPF authentication. We can either do that at the interface level, or we can do it per area. And then we're going to set up the keying material. That is our authentication key. It doesn't matter which one you do first. Both of them have to be completed in order for authentication to work. When authentication is configured, in essence, what's going to occur is that the router is going to generate its messages as it normally would, and it's going to take that data, a hello packet, an update, a link state update, or a link state request, and it is going to generate a hash of that information along with the keying material that we configure, and the output of that hashing process will provide us a MAC, a message authentication code. And then that message authentication code will be encapsulated into the OSPF header. You'll notice that we see that in the diagram here. The message body is the payload of the OSPF message, the specific message, and the green section indicates our standard 24-byte or 16-byte OSPF header. And in this case, we're looking at a 24-byte header because of the it's OSPF v2 in this case, right? So we've got our header, and the authentication type would indicate the authentication method that we're using. A 0 would indicate no authentication, a 1 would indicate plain text authentication, and a 2 would indicate message digest authentication. And then that 32-bit authentication body, or that last field in that green section, would actually contain the authentication data. All right. By default, authentication is not enabled. Certainly, it's highly recommended if you're going to implement these protocols to prevent route injection attacks, route spoofing attacks, and so on. So again, as I mentioned before, authentication type of 0, if you go into a Wireshark capture and you look at your OSPF packet header, you'll see that listed in this section right here. 1 is clear text authentication, where the password would actually be incorporated into this field. And then number 2 would be cryptographic authentication, which is based on a hashing algorithm, specifically MD5 with classic mode. Okay? If you look at the authentication of the message itself, now it indicates here it's a 64-bit field, which is actually kind of interesting because it indicates that it is a 32-bit field in this particular case, right? Those numbers along the top indicate the size of the field. So actually, let me pull up a authentication, a Wireshark message here, because, you know, if ever there's kind of any indication that something might be documented incorrectly or whatnot, it's always good to go back to the original source and look at the actual captures. So we see in this particular case that we have authentication type of 2, which indicates cryptographic authentication. There is our key ID, which appears to be an 8-bit field. And then there's a cryptographic data length. And then this is the actual cryptographic data. So it actually does look like it is, in fact, a 64-bit field. We can see that over on the right side in the hex dump. We have a sequence number as well. So it looks like in this particular case that this diagram is not really representative of what's actually included. So there should be some more rows, if you will, for that authentication field. But again, that's always kind of a good thing. If you doubt what a book is telling you, or you doubt what maybe an image is showing you, go look at that Wireshark capture and take a look at those fields so you can see what it actually looks like in real life, right? So 64-bit field, the clear text key, if we're doing simple password authentication. Clearly, that's not going to be your best option. We don't want to be able to see the secret key in a Wireshark capture, or the hash key and message if there is MD5 authentication, which we saw previously. So if I'm running MD5 authentication, that's message digest 5. And by the way, most people will say, well, that's kind of an obsoleted hashing algorithm. In most cases, we're trying to use SHA. If we were talking about a data in motion cryptographic process, I would say that's probably true, that MD5 should be avoided and SHA should be used because we want that at minimum of 160-bit or 160-bit message authentication code. But for the purposes of router authentication, it will suffice. You know, these cryptographic hashes are generally secure. They're one-way functions, and it's still computationally expensive to kind of revert that hash, especially if you're using a secure password in the configuration process. All right. So the hashing algorithm does those binary calculations based on the OSPF packet, which includes the OSPF packet header and the payload of the OSPF packet. It does not include any of the authentication component does not include any of the underlying layers, right? We're not going to include the IP header or the data link layer header in the hashing process because those will change as you move through the network. But certainly the OSPF header and the payload will be utilized. So a value of 2, as we saw in the Wireshark capture, indicates the authentication of cryptographic authentication, and then we see that information. The hash value gets transmitted inside the packet, even though the packet is sent in the clear. We also saw the key ID. In our particular case, we were using key 0. we can actually create keychains like we did with the EIGRP authentication and specify different key IDs and key strings. But if we're just simply applying the key to the interface, that's going to default to key ID 0. And then we see a non-decreasing sequence number, which is utilized for identifying the sequence of the authentication packets themselves. So in that exchange process, if you will. All right, and that's to protect against replay attacks. So somebody can't simply capture one of those OSPF packets, modify the data, and resend it with the same sequence and authentication string, because the sequence number would not be valid, and so that provides anti-replay protection as well. So the receiver knows the password because that password has been configured on the receiver. It's going to use that password to calculate its own hash value. And if nothing has been modified in the message, two things are happening. Number one, we're verifying the integrity of the message. And number two, we're verifying the authenticity of the the sender, right? Not individually, right? Because we're sharing keys, but I suppose you could technically identify the sender individually if you're using different plain text keys or authentication keys, I should say, between different peers. You'll notice that the key, even though the authentication method can be specified at the interface level or in the OSPF routing level, as you can see here, authentication, we apply the key to the interface in both cases, which means that key only applies to that adjacency. Now, you can use the same key for other peers, but generally it's recommended to have different keys for different peering sessions just to protect those individual sessions. Now, because we specified IP OSPF authentication, in this particular case, we are using an authentication of 1, which is plain text authentication, which is why the key is listed as plain text. Again, not recommended. And by the way, you would see that key in the configuration file as well. Even if you run service password encryption, which uses a Vigenère, an old World War II French encryption algorithm, the Vigenère algorithm, to encrypt the plain text information, everybody pretty much knows these days that those level 7 encryptions that are used by or that are facilitated by service password encryption are not really secure. We can pretty much find out what those passwords are relatively easily. So in every sense, it's best just to avoid type 1 authentication, plain text authentication. If we want to switch to OSPF v2 MD5 authentication, all we simply have to do is specify a key ID and specify the key or algorithm or the hashing algorithm, in this case MD5, and then finally specify the secret key. The secret key is never published. It's not transmitted, so it's very important that the key ID and the key string match on both sides. Doesn't really matter what the key ID number is, as long as the same key ID that's being used to send the data with the hash is the same key ID that's being used to verify the data on the receiving side. When we get it, you can get into time-based authentication as well, like we did with the EIGRP, but we don't really talk about that in this section here. All right. So the key ID, which is an arbitrary number, it is not just locally significant. We have to have a password recommended a password of 16 characters. The Cisco iOS will accept shorter passwords, and spaces are allowed, so you can actually use passphrases as well, which generally tends to be a little bit more secure because those passphrases can be much larger. But at a minimum 16 characters. The key ID is used to generate the message digest, and then the packets themselves, message digest is going to be appended to the packet in the OSPF packet header, and then that's going to be sent over so that we can verify it on the other side. That key ID allows for transitions between keys as well. We saw this in the context of EIGRP, where we could establish a key chain and we can have multiple keys on the keychain, each key string represented with their own unique key ID. So what we would do is we configure multiple key IDs, maybe 12 key IDs if we're going to switch one for every month, or 52 key IDs if we're going to do one every week. It depends on what the level of security you want to provide. And then those key IDs would overlap slightly, just in the event that we may have a situation where clocks are not synchronized between devices and whatnot. We don't want a timing synchronization issue to invalidate a key when it's supposed to be valid for a particular period of time. All right. All right. And we saw the configuration was relatively basic. All right. Go back to it real quick here. We see that under the interface, we are implementing the message digest authentication, and we're specifying the MD5 hashing digest key and secret key. Notice that we can also implement IP or area authentication under the router process as well. If you do specify the authentication of message digest under the area, there's no need to put that command on the interface. And I believe, if I am not mistaken, I probably need to go look this up, but the area configuration would override whatever would be configured on the interface level. It's not typical, right? Typically the interface level overrides the area configuration, but all right. So we are going to jump into our next discovery, Discovery 9, configuring OSPF authentication.
So our last discovery for today, Discovery 9, configuring authentication. Again, we're working with OSPF v3 in this case, so it's going to be slightly different than your classic authentication configurations. We're going to learn how to configure authentication in our OSPF v3 network. The link between router 1 and router 2 is going to be using IPsec AH. Now there's two ways to implement IPsec. Again, this is native to IPv6, and because our transport is only IPv6 in OSPF v3, we don't need to worry about configuring authentication for v4. Remember, with OSPF v3 address family mode, everything is transported over v6, so we only have to authenticate v6 in this case. And there's two ways that you can implement IPsec. AH is authentication header, which means we're going to authenticate the packets only. We're not going to encrypt the packets. ESP is the encapsulated security payload, encryption. I always say the E stands for encryption and the A stands for authentication. It actually stands for encapsulated security payload, but when you add ESP on top of it, now you're doing encryption as well, which normally is something that's not available with the protocols. Normally you don't have the ability to add encryption and authentication. But because we're utilizing the extension headers in IPv6, we can do this. All right? So we're going to do a basic AH authentication between R1 and R2. And then between R1 and R3, we're going to do our AH plus ESP. You, I guess, could technically do just ESP without AH, but I mean, part of our goal here is to authenticate the messages from the peer. Finally, the entire backbone area will be configured with cryptographic authentication using keychains. Remember, I said you could use keychains with OSPF just like we used keychains with EIGRP. We'll have access to all four routers. They're all pre-configured with OSPF. Our first task, AH between router 1 and router 2. Our second task, ESP between router 1 and router 3. And our final task, HMAC SHA 256 for area 0. By the way, SHA HMAC, this is a hashed message authentication code, is what HMAC stands for. Basically, you can run hashing without secret sauce, without a key, or you can run hashing with a key. Regular hashing is just SHA or MD5. Anytime you add some sort of keying material to the hashing process, that's where you always see the HMAC tied to it. So HMAC MD5 means there's some sort of keying material added. HMAC SHA means there's some sort of keying material added. All right? So it's really the MAC, the message authentication code, is the authentication piece. SHA itself is not an authentication protocol. It's an integrity protocol. MD5 is an integrity protocol, but we're adding the authentication by putting in that secret sauce, by putting the key into the hashing process. That's what creates this HMAC scenario. It's not a really technical way of describing it, but whenever you see HMAC, you know that that involves some sort of keying process as well. All right, there's our topology. These are our addresses. Again, always Ethernet 1/whatever. And do we have any serials? We don't have any serials in this case, so it's all Ethernet. So task 1, configure OSPF v3 IPsec AH between router 1 and router 2. Authentication and encryption are used to secure routing updates. The idea is that we're trying to prevent somebody from sticking a router in our network and doing what we call a route injection attack, where they're injecting false routing. Maybe they're injecting longer prefixes so they can influence how packets get routed. Maybe they're creating black holes in the network by injecting routes that don't go anywhere. Maybe they're trying to establish unauthorized neighbor adjacencies and so on. OSPF v3, as I mentioned in the lecture, uses the native IPsec functionality built into IPv6. I don't know if you guys had a chance to deal with cryptography too much, but I have like an 8-hour cryptography video on my YouTube channel. It goes through everything. But so if you're interested in cryptography, it's under the CISSP group. But IPsec is a whole framework of protocols. We've got hashing algorithms. We've got, for message integrity, we've got cryptographic algorithms for confidentiality. We've got authentication algorithms for peer authentication like RSA or DSA. We've got key exchange algorithms like Diffie-Hellman for doing key exchange and establishing secure tunnels. So it's actually IPsec itself is not a protocol. It's a whole suite of protocols that we can combine together to provide this IP security, IPsec, right? In IPv6, this functionality is built in by default. It's what we call an extension header in IPv6. We'll do some Wireshark captures when we get everything set up. We'll take a look at what those extension headers look like. It's beyond the scope of this lesson here, but what the heck? We're going to configure it, might as well look at it. So OSPF can either do AH or it can do ESP or it can do a combination of both. If you're not concerned about confidentiality, you don't want encryption, then you can do number 1. If you're concerned about authentication and encryption, then you have to do both. We'll see an example of that. That's our second task. So the security policy for the router that we have to set our key. Obviously, the key is going to be that secret sauce that goes into the hashing process. And we also have to set what we call a security parameter index value. That's used for the encryption piece, for the ESP piece. You'll see what that is. It's a long string of numbers and characters that we use basically to establish the cryptography between the peers. OSPF v3, which is RFC 5340, requires the use of IPsec to enable authentication. You have to have a crypto image. How do I know if I have a crypto image? I'm looking for a K9 in the image name, right? I don't know because we're running iOS V show version if we are going to have a K9 necessarily. Yeah, we do have a K9 here, right? So that K9 in the image name indicates that iOS image supports cryptographic functions. If you don't have the K9, you won't be able to do this stuff. So make sure if you're getting an image for a router or you're adding an image to GNS3 or whatever, make sure you have that K9 cryptographic feature. If you recall, I don't know if you guys know this or not, but cryptography is included in the Wassenaar Agreement, which is the munitions and export restrictions that they have for munitions and whatnot that came from the Cold War and World War II. All the Warsaw Pact countries came together and said, we're going to restrict the sale of arms and all that. Well, cryptography was added to that some time ago. So there's, certain areas where you might not even be able to get this functionality. All right. So some images don't have K9 because you still want to be able to have iOS in those countries, but they're not allowed to have cryptography. So I guess they can have their own, but they're not allowed to get it from us. All right. And actually, I think it even says it. I don't know if it, yeah, it says it right here. This product contains cryptographic features and is subject to laws governing the import and export and transport. So that's another thing to be careful. Don't grab a router with a K9 image and send it to Syria, because then you'll get arrested. No. It's kind of interesting how that's documented, but that's actually, you know, I would say federal law, but it's also globally restricted. All right, that's why people were getting so upset about WhatsApp, because WhatsApp encrypts everything, and they're saying, no, you're not allowed to do that because you're in a country that's not allowed to have encryption. It's kind of weird. All right. When OSPF v3 runs on IPv6, it requires IPsec, or excuse me, IPv6 AH or IPv6 ESP headers, which are called extension headers. The actual IPv6 header is fixed, but we add extensions to the v6 header to add different features. To ensure integrity, that's the AH piece, authentication, the AH piece, and confidentiality, the ESP piece. All right? So integrity and authentication are authentication header. Confidentiality is the ESP header. All right? These extension headers can be used to provide those functions. All right? To use AH, we use the OSPF v3 authentication command. To use the ESP function, we use the OSPF v3 encryption command. It's not quite that simple. There's actually a couple of different commands that we have to execute. Like, for example, to do IPsec with encryption, we have to have an SPI defined, as well as our integrity key and our hashing key. And the SPI value, the security parameter index, is what's used to provide the encryption. We do not have to set up traditional IPsec. We're not like setting up a VPN tunnel between the routers, because we're not encrypting everything. We're only encrypting OSPF. So it's not like we're setting up a VPN tunnel between the two routers and then just all the packets and all the routed packets and routing packets get encrypted. Because in that case, you'd have to set up ISA-KMP, you'd have to set up you know, phase 1 properties, you'd have to set up phase 2, all that stuff. We're not going to be doing all that in this case. All right, we're just going to be using the native IPsec features built into IPv6. So the first thing is, on router 1, we're going to go into our interface. Remember, it's 1.1 in our case, interface Ethernet 1.1. And we're doing the authentication on this. We're setting up an SPI 256 SHA-1. All right. Now, the actual SPI number is 256. The actual key is this value right here. All right. So we're actually specifying the key that's being used. This is for encryption on router 2. This is for authentication on router 1. So this, you might want to use the cut and paste feature if you've got the PDF open, because it's easy to make a mistake. They're just using incremental numbers there, but we want to make sure that we're using the right numbers. On which one? The first command? SPI? Okay. Yeah, you have to set the key. So let's go into interface Ethernet 1.1. Yeah, the password's down here. Remember, that's the key that we're using. It's just not in bold. Yep, you need that key. That's a typo, actually. I need to fix that. I mean, it's not really a typo, but so now I need to do this. Let me actually do this and copy just this part. And then we paste that. There we go. All right, this is the actual key that we're using. Now notice, as soon as I did that, it actually enabled ISA-KMP. I didn't configure any ISA-KMP properties. ISA-KMP is a Internet Security Association key management protocol. That's basically what allows us to do the cryptography, but because we're using IPv6, it's kind of built in. All right, so I'm going to do that on router 1 and router 2, and then we should be good to go. Interface Ethernet 1.0 on router 2. And let's see if I can, we lost our adjacency because we only configured one side. By the way, SHA-1 uses a 160-bit key. So these numbers represent that key. Obviously, you'd want to use a different key than 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. All right. But notice we got our adjacency back. All right. And you'll also notice we didn't really have to do anything else. That was pretty much it. So what I'm going to do is I'm going to do a packet capture on that link. Let me get rid of all these other ones here. Get rid of all these different packet captures. And let me go to GNS3. And we're doing this on router 1 and router 2. I just want to show you what the packet header would look like now that we've enabled authentication. Not encryption, but authentication. All right. So here's the hello packet. This is from router 2. And if you look at the actual header and the hello packet, we don't see anything in the packet that indicates authentication is configured. In classic mode, we would. In OSPF classic mode, I would see authentication type. I would see the authentication hash. But in this case, the authentication is here as an extension header in the IP packet header. So this is my original 40-byte IPv6 packet header. This is the IPv6 AH extension header. So it's saying, okay, the next packet is 89. This is the SPI. This is the sequence. This is my ICV, etc. So we, you know, I don't have to get into what these elements are, right? But my point is that now authentication is not really part of OSPF. Authentication is being provided by IP. All right. Even though it is configured on the interface. But you notice the command itself, yeah, it references OSPF, but it's still carried inside of IP. To ensure that OSPF v3 authentication is applied only to the connected link, use the OSPF v3 authentication IPsec SPI command in interface configuration mode. R1 and R2 are configured with the same SPI, which by the way is 256. That's a number that we chose. That's not 256-bit hash. That's just a number that we chose. All right. SHA-1 is 40 characters. If you do 40 characters times 4, 160 bits. They're hexadecimal characters. So you could have A through H as well. They just didn't do that. They don't want to make it too complex if you had to manually type it in. 32 characters for MD5. So if you do 32 times 4, 128-bit hash. Okay? So SHA-1 is 160-bit hash. MD5 is 128-bit hash. And this is basically the numbers. So that's a hex 1, hex 2, hex 3, blah, blah, blah. And we could have used A through F as well. All right. So you can't just create a passphrase that's 40 characters long. It have to be hexadecimal characters. All right. That's pretty important. They don't really mention that in the book, but that's what those 40 characters are. All right. To apply authentication policy, if it was to do this on the area, we didn't do it on the area, but you could. You would do it under the router OSPF address family configuration, and you can apply the authentication to the whole area, which might be beneficial if you have a whole bunch of peers in that area. You don't want to do it on every single interface. You could apply the authentication to the area. All right. We did lose our adjacency temporarily. So let's see what's going on with our cryptography here. They're using the command show crypto IPsec SA. This stands for security association. And what we're looking for here is packets that are being processed through the IPsec process, right? in this case being authenticated through IPsec. This is the policy based on the fact that we chose 256 for our SPI. Let me run the command actually. Do show crypto. You can also do ISA-KMP SA if you wanted to see phase 1, but we don't have traditional IPsec configured. If this was traditional IPsec, I would try to verify if phase 1 is working and phase 2. But in our case, we're just using the stuff that's built directly into IPv6. So, oops, show crypto IPsec SA. All right. Local address is my link local address to get to the other peer. This is the interface that it's tied to. Notice it did create a crypto map tag. Typically, if you're doing traditional IPsec, you have to create a crypto map and then you have to apply it to the interface. This is the local identity. This is the remote identity. All right. FE80 to anybody. Right. 89 is the protocol ID. I'm not sure what the 10 is. Oh, I know what the 10 is. That's the subnet mask. FE80 link local addresses have a subnet mask of 10. Default route has a subnet mask of /0. So this is the address and subnet mask. Sorry? Oh, it does say that right there. Yeah, how about that? Again, like I said, it's been a long day. All right. Current peer, FF02:5, which is all OSPF routers. Port number is 500. That's actually a well-known port for authentication. All right. And then we can see encaps and decaps and encrypt and decrypt. Now, this does not mean in this case packets encrypted and packets decrypted for confidentiality. This means packets encrypted and decrypted to perform the hashing function, the digest, if you will. So I've digested 97 packets and I've verified 85 packets, which means I'm authenticating these packets. All right. And then we see our local crypto endpoint is our local link local address. The remote crypto endpoint is the OSPF all routers endpoint. And then we see our SPI. We define the SPI. We should have an inbound and outbound. The numbers don't have to match, but it kind of makes sense to make them match. We're using transport mode as opposed to tunnel mode, which is fine for peer-to-peer authentication. We're using SHA HMAC for our transform set, and so on. And there's no volume rekey set, meaning there's no the lifetime is seconds are set to 0. Volume rekey is not set, which means that there's no lifetime established for this tunnel, for this cryptographic process. All right. The key here, no pun intended, but the thing that you're looking for here is really this section right here. That's what you're looking for. Are the packets being processed through the cryptographic process? Because you can create cryptographic functions and then you might not see them being authenticated. But what's the other key? The other key is that I have a neighbor. If I don't have a neighbor, most likely I've mistyped a key or I've misconfigured the authentication. If I have a neighbor, then authentication must be working. Assuming you had a neighbor before you implemented authentication. All right? All right. If I do show SPF interface, this works in classic mode as well. Do show OSPF v3 interface. You should be able to see on the interface that authentication is configured. So let me go back up to the right interface. Right, which interface? It's the 1.1, I think. Yeah, 1.1. Well, it depends which router you're on. I'm on router 1, so it's going to be 1.1, and you can see it right here. SHA authentication SPI secure socket is up. That's another thing you're looking for. Make sure that the secure tunnel, the security tunnel is up and operational. Okay. SPIs do not have to match. SPIs are sent in either direction. Now, here's the thing though. You would have to have, if you had separate SPIs on each side, you would have to have 2 lines to identify the authentication. Because for the inbound, I have to match an SPI. For the outbound, I have to match an SPI. So it just makes sense to make them match. So you only have to define one. All right? All right. You can examine the IPsec essays that you've applied using the show crypto IPsec essay command. The command displays the policy name. In this example, OSPF v3-256, the protocol number, protocol 89, meaning OSPF. And both OSPF v2 and v3 use the same protocol. The command output includes packet statistics that indicates that AH is used to protect the OSPF v3 traffic. ESP is not used because encryption of the packets has not been enabled. Is there a way for us to see that in the show crypto output? Not really. Well, the port number might indicate that. When we add, you'll see the port number might change when we add our encryption. But I'm trying to see if, yeah, this is another way to tell. No ESP statistics. Remember, ESP is encryption, AH is authentication. So we know that we didn't enable encryption here because we're not seeing an ESP SPI. We're only seeing an encryption SPI. Okay? Between router 1 and router 3, we want to configure ESP. Notice that we're now using the ESP keyword. We have to specify an encryption algorithm. In this case, AES CBC 128. That's AES, Advanced Encryption Standard with cipher block chaining with 128-bit key space, 128-bit encryption. So go to router 1, and in this case, it's interface 1.2. Interface Ethernet 1.2. And I'm not typing all that in. I'm going to cut and paste it again. The 257 is an arbitrary number that we can choose, as long as it matches on both sides, since we're only defining one thing. Now, notice there's 2 keys here. You have one key that's used for the encryption. That's my 128-bit key. And then you have your 160-bit key that's used for authentication. So you're specifying 2 separate keys in this particular case. Again, these are hexadecimal characters, 4 bits each. So they have to add up to the total, the full amount, the full string. Show run pipe. Let me do a show run pipe include ESP. And I should be able to just copy this whole line and then go to router 3. On router 3, it's going to be interface 1.0. And I'll paste that in. You guys understand what I'm saying about the 2 different keys? This key, notice it's a shorter key. This key is used for the encryption, which is a 128-bit encryption algorithm. So that would be 128 divided by 4. So a 32-character key. And this is my 160-bit key, which is used for SHA-1. So this is my hashing key. This is my encryption key, which makes sense, right? Because AES followed by the key, SHA followed by the key. Could I do something besides AES 128? Absolutely. We should be able to go all the way up to 256, maybe even 512. Nope, just 256 in this case. Which, by the way, would probably be recommended. But we're doubling the size of the key space, which means hopefully the algorithm is going to be a little bit more secure. So it's not difficult to do. I mean, the configuration is relatively simple. How do we verify it? Same thing. At least now when you're looking at this table, you understand why they say that characters have to be a certain length. 16 bits, 16 characters for DES means that we're using a 64-bit key. Triple DES is 48 characters, which doesn't quite make sense if you think about it, because it's only 192 bits. You would think it would be 3 times this, but we use the same, in some implementations of triple DES, we use the same key twice. We use the first and last key are the same, and the middle key is different. For SHA, it's going to be 40 characters, 40 times 4 is 160. MD5, 32 characters, 32 times 4 is 128. And then same thing for here, 128, 48 characters there, and 64 characters there. At least now you know why those numbers are what they are, because we're multiplying 4 times the length, because they're hexadecimal characters. Okay? We can also apply this encryption to the area just like we did with AH. But now note when I do a show crypto IPsec SA, I'm going to see ESP characteristics as well. We still see the same encap and decap and encrypt and decrypt. Port 500, this is for the remote peer of FF02, ;5, and that's the one without encryption. Notice here, we have an ESP SPI now. AES is the transform with SHA HMAC. And initialization vector, we don't have to get into that. That's part of the CBC process, the cipher block chaining process. In my CISSP cryptography thing, I talk all about block chaining and what that does. All right. So we have an outbound SPI. We have an inbound SPI. And we're seeing our encap and decap and our encrypt and decrypt. Let me go right back up here, right here. All right. With encryption, we can also enable things like perfect forward secrecy. That just has to do with randomizing the keys through the process. Let's get a capture real quick from router 1. Let me actually start the capture to router 3. I just want to show you what the extension header looks like. You can pretty much imagine we're still going to have our AH header, but now we're going to have another header called the ESP header that's part of IPv6. The OSPF packet still looks the same. It's not going to look any different. All right. Actually, we won't see the OSPF packet now, will we? It's encrypted. That's why it's all gray. It's all gray because it's all encrypted. That's cool. All right. So here's our IP header. And here's our ESP data. ESP encrypts part of the IP header as well, especially if we're using tunnel mode. We have an outside IP header that's used for transport, for transporting the packets. And then notice the next header here is not OSPF. The next header is protocol 50, which is ESP. So we can't even see the extension headers in this case because they're encrypted. Whereas with AH, let me see if I can grab an AH one. Notice the protocol here is 51. Protocol 51 is AH, but it's not encrypted. We can still see it. All right. Let's see here. Show us interface. Again, I'm not going to run the command, but obviously we're looking at this piece right here. AES CBC 128, SHA-1 Authentication SPI 257. All right. So the last task, configure OSPF v3 HMAC SHA-256 authentication for the whole area. it's going to be pretty much the same configuration that we had before, but instead of applying this to just an interface and a peer, we're going to apply the authentication to the whole area. All right. Notice it also says authentication, OSPF authentication is used for non-IPsec cryptographic authentication. So this is what's natively built into OSPF v3. All right. So it adds a new data block using a TLV to OSPF v3. It's signaled to the neighbors, AT standing for authentication. We define a keychain. We enable the keychain on the interface for the area. We're probably going to do it on the area in this case since we're doing it for the whole area. So unlike OSPF v2, OSPF v3 does not include the auth type or authentication fields in the headers. We already saw that when we were doing our captures. Instead, OSPF v3 relies on the IPsec protocols. Again, we saw that in the previous discussion. RFC 4552 describes how the IPv6 AH and ESP extension headers can be used. OSPF v3 authentication trailer, AT is authentication trailer, which was defined in RFC 7166. So this is a newer specification. Anytime the RFC number is older or higher, excuse me, anytime that RFC number is higher, it's going to indicate that it's a newer standard. Adds support for SHA, including SHA-1 and the new, what we call the Suite B protocols, SHA-224, SHA-256, SHA-384, and SHA-512. Hashed message authentication code. Remember what I said about that? That means we have some sort of keying material that's combined with the hashing process to provide us authentication. So basically what they're saying is this authentication trailer piece was added so that we don't have to rely on the IPv6 security extensions. All right? You can see it's a relatively new concept. 15.4.3, uh-oh. No bueno. What are we running? 15.2.4. I don't think it's going to work in our routers. Yeah, so we're just going to have to do a review here. It's not going to work in our routers. So we'll just have to review the configuration here. So this is really new, right? Not really, really new, but definitely newer than what we have. All right. OSPF v3 devices append a special data block called the authentication trailer to the end of the OSPF v3 packet. The authentication trailer is introduced in the OSPF v3 options field. Basically, it's almost like an OSPF v3 extension. And we can do that because the program, the protocol is extensible. It's always been extensible. So how would we configure this? On router 1 and router 4, we would set up our keys. So this is just like an EIGRP keychain. This part would work. You could actually do the keys. You just would have a problem with this right here. It won't take that command, the cryptographic algorithm. So you can actually come into the router and do the keys. Yours might work actually. Does yours have? Yours has the right iOS. Yeah. He's using the online version of the labs. So it does allow us to do the keys, but this particular iOS, I'm going to have to see if I can upgrade.
That's what we pay for. Like
Yeah.
Viral Labs?
No, it's not viral, but he's doing the continuing education, so he gets access to the online labs. So, which is viral. That's what they're running is viral. I could probably, and I'll probably do this actually, rebuild this lab with that new iOS, but it would require that you guys also install that appliance with that new iOS. So we're not going to do that right now. That would take a long time. All right. But we're just specifying the algorithm. Here's the key and here's the key string. So this is not foreign to us, right? This is standard peer authentication with a key ID and a key string, just like what we did with the IGRP. The only thing that's not available to us is the ability to run this Suite B hashing process, this HMAC SHA-256. So how do we verify that the keychain is valid? Show keychain. just like we did with the EIGRP. Remember in EIGRP, we were able to specify a send and accept lifetime? We can do the same thing with these keys, and we can have rotating keys. We can have keys that expire and become active over time so that we can identify which keys are valid over what period of time. Then all we need to do is apply the keychain to the area. Now this command actually should work. If I did this, it's going to break my configuration, but if I was to apply this, it should actually work. The only difference is we would not be able to do the SHA-256. We could only do MD5 because MD5 has always been available with OSPF.
Seems like it wants us to set up the Ipsec SPI with this.
Yeah, it didn't allow the keychain here. Yep. Yeah, it's a version issue, yeah. So, but again, we apply the keychain. It's just going to say, okay, we're going to use this set of keys that we've defined in the keychain, but now it's applied to the whole area. So any relationship that router 1 has to any router in area 0 would have to have the same configuration. So rather than doing it on a per interface basis, we're doing it on a per neighbor basis, right? All right. So this is just applying the same configuration to the other side, to router 1, which is also part of our area 0. So we're doing this on router 4 and router 1. Verify that the keys are valid. Again, as I've always stated, when it comes to ensuring that the keys work, what's important? Timing, right? You need to make sure that the times are correct. Otherwise, your keys may not be valid when they're supposed to be. And then apply the authentication to the area, and then the neighbors should come back up. Same thing on router 4. Neighbors should come back up, and you should be good to go. Show OSPF interface. We can now see that we're running cryptographic authentication. The sending SA, security association, is key 1. Algorithm is SHA-256 using keychain OSPF keys. Again, the key ID and the key string have to match. The keychain names do not have to match between the routers. Key ID and the key string have to match. Key string names or keychain names do not have to match. All right, so we'll wrap up this discovery. We'll see you guys in the next one.
All right, so the last thing we're going to talk about before we get into troubleshooting OSPF is what is an OSPF virtual link? I kind of hinted at this configuration option when we were talking about the requirements for OSPF and in some of the earlier sections. There may be instances where you may not be able to meet, initially at least, the design requirements that we have for either a contiguous area 0 or backbone, or to have all of your non-contiguous areas directly connected to the backbone. Maybe you're in the process of joining two companies together and area 0 is divided, like we see in this diagram here, by another area. Or, you know, there's another scenario where an area might be discontiguous from the backbone, like actually what we see in this example, sorry. Area 20 is not connected to the area, to the backbone area, and has another area in between. So there is a solution for this, albeit Cisco recommends that this is only a temporary solution, and that is to create something called a virtual link. That virtual link allows us to virtually tie that discontiguous area to either the backbone or, in this example, it would work this way as well. Let's say this is not area 20, but this is area 0, right? And we would have area 10 with two area 0s essentially. We could join both area 0s together with this same technology. It does pose a bit of a problem for some other concepts in OSPF, but in the short term, this is a good solution to get the network functioning and to get it operational. All right. Now, there's a couple of rules when it comes to creating these virtual links. First of all, the virtual links are configured only on the ABRs. It doesn't matter how many routers you have in between those two ABRs. In our example, we only have a couple of routers in the area 10, but that virtual link can span as many routers as necessary within a single area. All right. The configuration of the virtual link is accomplished by configuring the virtual link configuration on the ABRs that allow us to bridge the discontiguous area to area 0 in this particular case. The second thing to consider is that you can only do this across one area. You cannot create multiple virtual links. Say area 20 was 2 or 3 areas away from area 0. You would only be able to create that virtual link between area 20 and area 0 across a single area. All right. Now, while it will work and while it will allow area 20 to become functional, again, this is only to be used as a temporary solution because there are some limitations. And while it's beyond the scope of this class to talk about what those specific limitations are, there are some limitations to having virtual links in your design. In essence, what we are doing is we are creating a tunnel through area 10 to make it appear as though area 20 has a direct connection to area 0 via ABR2. All right, as far as the configuration goes, it's relatively straightforward. We simply go into our ABRs and we specify the router IDs of those ABRs, of the neighboring ABR, I guess I should say, and specify that we're going to create a virtual link utilizing those ABRs. So in this case, we're creating an extension of the backbone. But like I said, we could also be using this to repair discontiguous area 0s where area 0 might be on the left and area 0 might be on the right, and then we have area 10 in the middle. So notice the configuration. This is for OSPF v2 Classic mode. I go under router OSPF and I say area, and then I specify the transit area. In this case, the transit area is area 10, virtual-link, and then I put in the termination point of the virtual link on the terminating ABR. So on ABR 1, I'm going to reference ABR 2.2.2.2, which is ABR 2. And then on ABR 2, I'm going to reference 1.1.1.1, which is ABR 1. There is nothing that you need to configure on the routers in between. This virtual link is established between the ABRs directly, regardless of how many hops or how many internal routers you might have to go through to establish that virtual link. Interestingly enough, this command structure would be exactly the same if it was IPv6. And the reason why is because we are referencing the router ID of the ABR. We're not referencing a specific interface. We're not referencing a specific IP address. We are referencing the router ID of the peer. And router IDs are written always as a dotted decimal number in 32-bit format. Okay? To verify the virtual link status, we can do a show Yeah, sure, go ahead.
Back to the diagram, please.
Yeah, sure, no problem.
Now, say there in area 10 there are more than 2 routers in there. Does it use the same OSPF selection process to select which link to go over, bandwidth being the deciding factor?
Well, as far as the way traffic traverses the area, it uses the standard mechanisms for cost calculations and bandwidth calculations to decide how traffic is going to flow. The only thing that this does is it allows area 20 to appear as though it's attached to area 0. Now, obviously, in that sense, we're still going to be learning about routes, from area 0. We're still going to have to be able to get to those destinations in area 0. So we're going to use the standard mechanisms for determining the appropriate path to reach area 0 that we would if it was just doing basic routing. So to answer your question, yes, you're correct. We're going to use the standard cost calculations to be able to identify the best path to reach area 0. Even though we have that logical virtual link, that traffic is being tunneled from ABR1 to ABR2, but we're still routing based on per destination routing and utilizing the physical link characteristics within area 10 to determine the best path. Does that make sense?
Thank you. Yes, it does. Thank you.
Yeah, no problem. No problem. All right. Now, if we are running OSPF v3, virtual links are only supported with the IPv6 address family configuration because the transport in OSPF v3 is IPv6. We would not be able, we would still use the same syntax. We'd still be specifying the router ID of the opposing ABR, but we would only do it under the IPv6 address family because we're only going to be establishing transport utilizing that IPv6 protocol. IPv4 is actually going to be encapsulated and run over that IPv6 transport in the case of OSPF v3. All right, so let's going to conclude this particular module. We're going to get into our next module, which is troubleshooting OSPF. We'll take a look at a lot of things about troubleshooting, and we'll take a look at a discovery in that module, so we'll see you there.